In 1958, NASA turned its eyes to a new frontier. For most of human history, the edge of space was an invisible boundary. But for NASA, it wasn't just a poetic horizon. It was a real frontier, one that hides strange and powerful forces shaping our planet, our technology, and even our survival. At this razor-thin line between air and vacuum, satellites teeter, auroras dance like ghosts, and mysterious bursts of energy flash in silence. When NASA set out to study this region, the so-called edge of space, they expected thin air and starlight. What they found instead was a dynamic electric realm full of surprises, a place where Earth and space are in constant conversation. So what did NASA discover at the edge of the universe? Before we begin the video, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below, and settle in for a journey to uncover what NASA found at the edge of the universe. The story of the James Webb Space Telescope began back in the 1990s. At first, the plan was simple: build it for about $1 billion and launch it into space by the year 2007. But that dream quickly turned into a long, twisting journey. Delays piled up, costs ballooned, and technical challenges kept sending the project back to the drawing board. Engineers and scientists faced problem after problem, some mechanical, some financial, and some simply the nature of doing something no one had ever done before. After years of waiting, redesigning and testing, the moment finally came in December of the year 2021. The James Webb Space Telescope, or JWST, rode into the heavens aboard a rocket, marking the beginning of a new era in astronomy. Yet even then, its work did not begin right away. Over the following months, it slowly unfolded itself in space, stretching its massive sunshield, powering up its systems and testing every delicate piece of hardware before daring to open its golden eyes to the universe. This giant of science weighs around 6,500 kilograms, about the weight of a large school bus. Its sunshield, a shimmering silver masterpiece, is roughly 14 meters by 21 meters, about the size of a tennis court. The main mirror, the heart of the telescope, is 6 times larger in area than the one on the famous Hubble Space Telescope. This means it can catch far more light, more photons, from the faintest, most distant corners of space, allowing it to produce images so sharp they feel almost unreal. James Webb carries an arsenal of cameras and scientific instruments designed to see in the infrared spectrum. This ability is not just a technological marvel, it is absolutely necessary. Because of the expansion of the universe, the light from the most distant galaxies has been stretched, or redshifted, until it is now all in the infrared range, no matter what it was when it first left those galaxies billions of years ago. That means an ordinary visible light telescope would see nothing but darkness where these galaxies glow. Infrared vision also allows James Webb to peer through thick clouds of cosmic dust that would block Hubble's view entirely. This makes the telescope not just a replacement for Hubble, but a partner. While Hubble mostly sees invisible light and some ultraviolet, James Webb focuses almost entirely on infrared and cannot detect certain colours of visible light at all. Instead of competing, the two telescopes complement each other, two sets of cosmic eyes working together to give us a deeper, richer view of the universe than either could alone. But enough about the hardware. Let's see what James Webb can really do. We will begin our journey in our own galaxy, then move outward, step by step, until we reach the far edge of the knowable universe. The sights along the way are nothing short of spectacular. Our first stop is a breathtaking region called the Cosmic Cliffs, part of a stellar nursery officially known as NGC 3324 in the Kuiper Nebula, about 7,600 light-years from Earth. What you see here are towering walls of gas and dust, each peak rising nearly 7 light-years high, vast enough to dwarf anything in our solar system. And this is only a small slice of the nebula. The entire structure is much larger, with a hollow centre where powerful stellar winds from young stars have swept away the surrounding dust, leaving behind a bubble-like cavity. Astronomers are drawn to this place because it holds clues to one of the greatest mysteries in astronomy: how stars are born. The intense winds push dust and gas into dense knots where gravity can take over, pulling the material together until nuclear fusion ignites and a new star begins to shine. But the process is shrouded in mystery, literally, because the same dust that helps form the stars also hides them from view. It's like trying to watch a bird hatch inside a closed egg. This is where James Webb's magic comes in. Using its mid-infrared instrument known as MIRI, the telescope can pierce through the dust, revealing details invisible to Hubble. The difference is astonishing. Where Hubble sees hazy outlines, Webb shows crisp detail, revealing the hidden structures and baby stars nestled inside. This new clarity will give scientists years' worth of data to study, helping them piece together the puzzle of star formation. If the cosmic cliffs show us the birth of stars, our next stop reveals the end of their lives. Closer to home, we turn our gaze to NGC 3132, better known as the Southern Ring Nebula. On the left, we see the nebula as captured by Webb's near-infrared camera. On the right, we see it through MIRI. At first glance, the term planetary nebula might make you think planets form here, but that is a misnomer. The name comes from early astronomers who thought these round clouds looked like planets through their telescopes. In truth, a planetary nebula forms when a dying star expels its outer layers into space, creating a glowing shell of dust and gas. Knowing what this ejected material is made of is essential for understanding the cosmic recycling process. The elements and compounds floating in these nebulae will one day become part of new stars, planets, and perhaps even life. Webb's ability to peel back the dust allows us to see the star systems inside with unprecedented clarity. We now know that the second star in this system has not yet expelled its own outer layers, meaning another nebula will eventually form here in the future. Webb also shows how the gravitational pull of the two stars stirs the nebula's dust into delicate, swirling patterns. From here, we will venture even farther, beyond our galaxy, to witness other stellar nurseries and cosmic wonders. But for now, you have seen how the James Webb Space Telescope reveals both the first breaths and the final size of stars, painting a story of the universe that was invisible to us before. Around 161,000 light-years away from our planet lies a celestial wonder called the Tarantula Nebula. Astronomers named it so because its sprawling clouds of gas and dust resemble the legs of a giant tarantula sprawled across an invisible silken web spun in the depths of space. While its beauty is enough to make any stargazer pause, scientists prize this nebula for another reason. It mirrors a chapter in the universe's distant past known as the Cosmic Noon. This era, which researchers believe occurred about 1 billion years after the universe first came into existence, was the most prolific period of star formation in cosmic history. Back then, stars were being born at an astonishing rate, and the Tarantula Nebula offers a living laboratory that may look much like that ancient, long-vanished time. Thanks to the James Webb Space Telescope, astronomers have been able to witness stars here in their infancy, mere cosmic newborns, making it an extraordinary place to study the earlier stages of stellar life. If we push our gaze further out into the universe, individual stars fade from sight, and we begin to see grander patterns, whole galaxies moving in a cosmic ballet. One such spectacle is Stephan's Quintet, a group of 5 galaxies. In truth, one of them only appears to be close to the others from our perspective on Earth, but 4 of them are genuine neighbours in space. This grouping became famous after appearing in the classic film It's a Wonderful Life. Astronomers think those 4 true companions are destined to collide in the far future. In fact, 2 of them are already in the process of merging, their immense gravitational pull flinging out waves of scorching hot dust as they twist and whirl around each other. The forces at play here are almost beyond human comprehension, and the energy released is staggering, a dance so vast that only the universe itself could provide the stage. The image of Stephan's Quintet that we see today is not a single snapshot. It is a painstaking mosaic, stitched together from nearly 1,000 separate images taken by James Webb. This method gives the final result breathtaking clarity, allowing astronomers to pick out fine details that would otherwise be lost. Now, let us venture even farther. We reach a point where even the mighty James Webb begins to strain at the limits of what it can see. One of its most famous achievements is an image called Webb's First Deep Field. The region captured here is so tiny that if you held a single grain of sand at arm's length against the night sky, that grain would completely cover it. At this incredible scale, almost nothing you see is a star. Most are entire galaxies, each one holding billions of stars within it. Some of the shapes appear stretched or warped due to gravitational lensing, where massive objects closer to us bend and distort the light from more distant galaxies lying far beyond them. In this image lies one of the oldest galaxies humanity has ever spotted. It is so unimaginably far away that the light it emitted when it first formed, just after the dawn of the universe, has only now arrived at Earth. By studying the faint reddish glow of this tiny speck, scientists can measure how much the light has been shifted by the expansion of space. This redshift tells them its distance, about 13.1 billion light-years away. Considering the universe itself is believed to be around 13.7 billion years old, this little galaxy is one of the earliest we will ever hope to see. You might be surprised, even disappointed at how small and faint it looks. But there's a reason for hope. When we compare this image to one taken by the Hubble Space Telescope of the same spot in the sky, Webb's advantage becomes clear. Hubble needed to stare at this region for 10 days straight to collect enough light for its version of the image. James Webb captured its own version in only half a day, a mere 1/20th of the time. Imagine what it could reveal if given the same amount of observing time as Hubble. That tiny red dot may only be the beginning. These images are not just scientific gold mines, they're also works of art painted by the cosmos itself. They left me in awe, but patience will be key. The James Webb Space Telescope has only just completed its delicate calibrations, allowing its instruments to cool to the perfect temperatures and ensuring every system works flawlessly. Over the next 5 to 10 years of its expected mission life, competition for its time will be fierce. Every second is precious, and scientists around the world are lining up to use it. Webb will be hunting for signs of life-friendly atmospheres on distant exoplanets, peeling back the veils of nebulae to watch stars being born, and comparing the sprawling ancient galaxies of today with the youthful, chaotic galaxies that filled the universe shortly after the Big Bang. With a tool as powerful as James Webb, we cannot yet imagine all the wonders it will reveal. The universe still holds its secrets, but for the first time we may finally be close enough to listen. Far away in the constellation of Scorpius lies one of the most breathtaking and mysterious objects in our sky, NGC 6302. Astronomers also call it the Bug Nebula, the Butterfly Nebula, or Caldwell 69, because its sprawling wing-like shape resembles either a delicate butterfly in flight or a strange cosmic insect. This nebula is what scientists call a bipolar planetary nebula, meaning it has two giant lobes of material streaming away from its centre, giving it an hourglass-like shape. The structure inside this nebula is among the most intricate ever seen in any planetary nebula, filled with glowing walls of gas, dense knots of material, and razor-sharp edges that look almost sculpted. At the heart of the Butterfly Nebula lies its central star, one of the hottest stars ever discovered, with a surface temperature of more than 250,000 degrees Celsius. This searing heat means the star it came from must have once been truly enormous. But today, this central star is a shrunken white dwarf, the burned-out core left after the outer layers were thrown off into space. Astronomers identified this hidden star in the year 2009 using the newly upgraded Wide-Field Camera 3 aboard the Hubble Space Telescope. It has a present mass of about 0.64 times the mass of our Sun and is wrapped in a dense dark ring of gas and dust. This thick ring has acted like a cosmic funnel, forcing the star's outflows into its striking bipolar, hourglass-like shape. NGC 6302 has been known to science for well over a century. It appears in the New General Catalogue, which means astronomers were aware of it by at least the year 1888. The earliest detailed study came in 1907, when astronomer Edward Emerson Barnard sketched and described its beauty. After the final servicing mission to the Hubble Space Telescope in September of 2009, the Butterfly Nebula appeared in some of the first spectacular images released, dazzling both scientists and the public. Its structure is more complex than it first appears. It has two main lobes, but there is evidence of an older second set of lobes, the ghostly remains of a previous eruption when the star was losing mass. Cutting across the middle of the nebula is a thick, dark lane that completely hides the central star from view at all wavelengths of light. One of the most dramatic features is its prominent northwestern lobe, which stretches about 3 arc minutes away from the central star. Astronomers believe this lobe was created by a violent eruption roughly 1,900 years ago. Its walls are expanding outward in a curious way. Each part moves faster the farther it is from the star. At a distance of 1.71 arc-minutes from the centre, gas in the lobe races away at 263 km per second. At the very edge, this speed soars past 600 km per second. The western edge of this lobe seems to have slammed into older clumps of gas, distorting its shape. The central star remained unseen for decades because of three obstacles. Its extreme heat means it shines mainly in ultraviolet light. The surrounding dust absorbs much of that light, and the nebula itself glows brightly, masking the faint star. Only when Hubble's new camera offered greater sensitivity and sharper vision did astronomers finally spot it. Its temperature is measured at about 200,000 Kelvin, and its mass is again confirmed at 0.64 solar masses. The original star was much heavier, but most of its mass was hurled into space when the nebula formed. It has now stopped nuclear fusion and is fading at a predicted rate of about 1% each year, slowly settling into its final life as a white dwarf. The dark lane in the middle has proven to be chemically fascinating. It contains unusual crystalline silicates, grains of crystalline water ice, and even quartz. Some features have been interpreted as the first detection of carbonates beyond our solar system, though this is controversial, since carbonates are usually formed in water-rich environments, which this nebula lacks. The debate remains unresolved. One of the most puzzling traits of the dust in NGC 6302 is that it contains both oxygen-rich silicate molecules and carbon-rich compounds called polycyclic aromatic hydrocarbons, or PAHs. Usually, a dying star is either oxygen-rich or carbon-rich, switching from one to the other late in life due to changes deep inside. This nebula belongs to a rare group where carbon-based molecules seem to have formed in an environment still rich in oxygen, a mystery that continues to intrigue astronomers. In the constellation of Ophiuchus, about 2,100 light-years from Earth, lies one of the most breathtaking cosmic sights ever captured, the object known as M29. Astronomers often call it the Butterfly Nebula, because its two elegant wings stretch into space like the delicate patterns of a butterfly in flight. But there is another, even more fitting nickname, the Twin Jet Nebula, which hints at its dramatic and powerful nature. When you look closely, M29 doesn't just resemble a butterfly. Its shape looks remarkably like two giant exhaust streams blasting away from an invisible engine. These jets are not just for show. The gas inside them is racing through space at speeds greater than 200 miles every single second. That's far faster than any earthly aircraft, and it's why astronomers say the comparison to a supersonic jet engine is spot on. From years of careful observations, scientists have learned that the nebula is growing larger over time. This means the violent outburst that created its twin lobes must have happened relatively recently, only about 1,200 years ago, which is the blink of an eye on the cosmic timescale. At the very heart of M29 is not one, but two stars locked together in an extremely close and dangerous embrace. They orbit each other so tightly that it is possible one star is partially swallowing the other. The stronger star's gravity tugs at the outer layers of its weaker companion, stealing streams of gas and flinging them outward into a dense, flattened disk that wraps around both stars like a cosmic skirt. This strange, spinning disk, which stretches to a size about 10 times the width of Pluto's orbit, acts like the nozzle of a gigantic space engine. High-speed stellar winds from one of the stars crash into the disk, and because the disk blocks most of the wind's path, the gas is forced to escape in two opposite directions. The result is a perfectly shaped pair of narrow, high-velocity jets shooting out into space, forming the butterfly's wings. The process is strikingly similar to how a jet engine works here on Earth. Inside the engine, burning gases expand, then slam against the engine walls, and are squeezed through a nozzle, producing powerful, focused streams of hot air. In M29, however, the nozzle is made of gas and dust, and the engine is a pair of dying stars in their final dance. The Hubble Space Telescope's Wide Field and Planetary Camera 2 captured this extraordinary sight on the 2nd of August in the year 1997. In the image, different colours reveal different elements. Neutral oxygen shines in deep red, once ionized nitrogen glows green, and twice ionized oxygen blazes in bright blue. Together they paint a portrait of a celestial engine at work, beautiful, violent, and fleeting. High in the Milky Way, inside a glowing cloud of gas and dust called NGC 6357, lies a bright cluster of young massive stars named Pismus 24. At the heart of this cluster shines its brightest jewel, a stellar system known as Pismus 24-1, also catalogued as HD 319718. This remarkable object is located roughly 6,500 light-years away from Earth. For a time, astronomers believed Pismus 24-1 was a single colossal star, possibly the most massive star ever discovered. Later, with sharper observations, they found that it is not one star at all, but at least 3 separate stars packed closely together. Each of these stars is still among the hottest, most luminous, and most massive known in our galaxy. The story of its discovery stretches back many decades. First, Pismus 24-1 was recorded under its HD catalogue number. Astronomers then realized that it should be separated into 2 different stars, Pismus 24-1 and a dimmer neighbor, Pismus 24-16. The bright nebula NGC 6357, which surrounds them, was already well known, but the tight cluster Pismus 24 itself was not recognized until the year 1959. In 1973, astronomers studied the cluster in detail and found 15 individual stars within it, of which 12 were judged to be true members of the group. The brightest of all was numbered first, Pismus 24-1, and it was initially suspected to be a gigantic supergiant star. Later observations revealed an even more complicated reality. The star was in fact a very close pair, an O3.5 supergiant in a spectroscopic binary system, and an O4 giant star orbiting about 500 astronomical units away. Even more precise imaging showed that Pismus 24-1 can be visually split into 2 main components, called NE, northeast, and SW, southwest, based on their positions. The NE component is slightly brighter and hotter than the SW component, and the NE itself is a spectroscopic binary, meaning 2 stars orbit so close together that they cannot be seen separately, but reveal their presence through the shifting of their spectral lines. This was unexpected, because the way the star's light is classified suggests they should each be brighter than they appear. Astronomers think that the NE pair's interaction might be affecting how its light is interpreted, or perhaps the SW star also hides a close companion of its own. Pismus 24-1 is also an eclipsing binary, with its brightness dipping every 2.4 days as one star passes in front of the other. The eclipses seem to come from the NE component, though scientists have not yet separated the light curves of the 2 main components. The eclipses are symmetrical, which suggests the orbit is nearly circular, and the 2 stars that cause them are almost twins in both mass and temperature. Star catalogues also note that Pismus 24-1 has 2 fainter companions, lying 5.5 and 16.4 arc-seconds away, which is not unusual given that the entire cluster spans only about 1.5 arc-minutes across. The NE pair cannot be individually resolved, but the way their eclipses behave shows that they are nearly identical, each with a temperature of about 42,000 kelvins. Together, they shine with nearly 800,000 times the light of our Sun, meaning each one alone is likely under 400,000 solar luminosities. The combined spectrum shows them as an O35 if type, a rare, massive star with strong nitrogen emission lines. And since no separate spectral signatures can be seen, both stars are thought to share the same type. As a single object, their combined mass would be about 74 times that of the Sun, but individually they are less massive. The system also produces intense X-ray radiation, probably caused by the fierce collision of stellar winds from the 2 supergiants. The SW component appears to be a single O4 giant star, about 40,000 kelvins hot, with emission lines of ionized nitrogen, silicon, and helium. It blazes with roughly 650,000 times the Sun's luminosity, has a radius about 17 times larger than the Sun's, and a mass around 66 times greater. Even though it is called a giant based on its spectrum, such hot O-type stars can show these features while still in the prime of life, burning hydrogen in their cores because of their intense convection and powerful stellar winds. When astronomers first modelled Pismus 24-1, before they knew it was actually multiple stars, They thought it might weigh over 300 times the Sun's mass, which is more than theory says should be possible for a single star to form naturally. As better telescopes and improved models of stellar atmospheres became available, this estimate dropped. The discovery that it was a binary and then a triple brought its total mass into a range that fits comfortably within what astrophysicists expect from star formation, without needing exotic explanations. For a while, astronomers thought that one of the stars here, Pismus 24-1, was the single most massive star ever found, nearly 300 times the mass of the Sun. But sharper observations revealed it was actually at least 3 stars, each still a staggering 100 solar masses. This star cluster is part of a larger structure, the nebula NGC 6357, a cosmic nursery where new stars are born. Inside, dense clouds of dark gas hide young protostars, the earliest phase of a star's life, as they slowly gather material from their parent molecular clouds. Others are wrapped in expanding cocoons of gas, making the whole region feel like a giant living organism in the process of creation. Next, we push much farther, to 60,000 light-years away, where we meet the globular cluster Palomar 12. Unlike most other globular clusters in the Milky Way, its stars are about 30% younger. The reason is that Palomar 12 didn't actually originate in our galaxy. It was born in the Sagittarius dwarf elliptical galaxy and only joined the Milky Way after a dramatic galactic encounter. Around 1,700,000,000 years ago, the Milky Way's gravity tore Palomar 12 away from its home galaxy. Even now, that galaxy is slowly being pulled apart by our own. When galaxies pass close or collide, gravity can twist them into bizarre shapes and steal their stars, exactly what happened here. But Hubble's reach extends much farther still. 30 million light-years away lies the Sombrero Galaxy, seen here edge-on. From this angle, we can clearly see its flat, disc-like shape, something common in spiral galaxies. The reason galaxies often take this form is because they spin, and the conservation of angular momentum causes matter to flatten into a disk over time. At the center of the Sombrero Galaxy shines a blindingly bright core, surrounded by lanes of cosmic dust that swirl outward like the brim of a hat, hence its name. 65 million light-years away, we find something stranger still, the diffuse galaxy NGC 1052, DF2. Its ghostly, see-through appearance comes from the fact that you can see distant galaxies shining right through it. Even more mysterious, it appears to have no dark matter at all, making it the first known galaxy of its kind. Scientists still aren't sure why. Travelling more than 300 million light-years, we arrive at the Coma Cluster, a gravitationally bound collection of over 1,000 galaxies. This cluster is also one of the first places where evidence for dark matter was found. Here, countless globular clusters float between galaxies, not bound to any single one but to the cluster as a whole. Far out in the depths of space, astronomers have found a truly remarkable star. Its official name is MAX J1149 Lensed Star 1, but most people know it by its more poetic nickname, Icarus. This star is a blue supergiant, an enormous and extremely hot type of star, and it was spotted not by ordinary means, but with the help of one of the universe's most fascinating tricks, gravitational lensing. Icarus holds a special place in astronomical history because it is the 7th most distant single star ever detected, following other far-off stars nicknamed Arendelle, Godzilla, Mothra, Quilla, Star 1, and Star 2. It lies about 14 billion light-years from Earth. For scientists, this measurement is linked to something called redshift, in this case z equals 1.49, which helps determine how far back in time we're looking. In terms of the universe's timeline, the light we see from Icarus began its journey roughly 9,340,000,000 years ago, when the cosmos itself was only about 4,400,000,000 years old, not long after the Big Bang in cosmic terms. Astronomer Patrick Kelly, one of the co-discoverers, explained just how extraordinary this find was. Icarus is at least 100 times farther than the most distant non-exploding star ever seen before it, a star named SDSSJ 1229 + 1122. It was also the first individual star to be spotted at such a distance thanks to the powerful magnifying effect of gravitational lensing, The discovery took place in April and May of the year 2018 while scientists were studying a supernova called SN Refsdal using the Hubble Space Telescope. Patrick Kelly from the University of Minnesota led the research team, and their groundbreaking findings were published in the journal Nature Astronomy. Although astronomers had been gathering images of SN Refsdal since 2004, it was only when they looked back through the data that they noticed something unusual. In pictures from 2013, a faint point of light appeared, and by 2016, it had grown dramatically brighter. This tiny point was not a galaxy, nor a quasar, nor a supernova. It was a lone star, magnified by more than 2,000 times by the bending of the light through gravity. This magnification came in two stages. First, the entire galaxy cluster Max J, 114, 9.5 plus 2, 2, 2, 3, located around 5 billion light-years from us, boosted the star's brightness by a factor of about 600. Then something even smaller and denser, possibly a star or a black hole about 3 times the mass of our Sun, drifted in front of the star's light path, producing an extra boost through a process known as gravitational microlensing. This second event, which peaked in May of 2016, made Icarus appear roughly 4 times brighter still. Interestingly, there was also a second brightness peak, which could mean Icarus is actually part of a binary star system. Normally, only vast cosmic objects like entire galaxies, blazing quasars, or the spectacular explosions of supernovae can be detected from such an incredible distance. But here, thanks to gravitational lensing, we could see a single steady star. Its temperature measurements confirmed that it was a blue supergiant. However, because the light we receive is stretched, or redshifted, by its long journey, Icarus does not appear blue to our eyes today, but instead shows a reddish or pinkish hue. When this light first left Icarus, the universe was only about 30% of its current age of 13,800,000,000 years. Kelly and his team believe that similar microlensing events could one day help us identify the very first stars that ever shone in the cosmos. The name Max J1149 comes from the Massive Cluster Survey, and refers to the star's coordinates based on the J2000 astronomical epoch. While Kelly had initially wanted to call the star Warhol, as a nod to Andy Warhol's famous saying about everyone having 15 minutes of fame, the team eventually settled on the name Icarus, inspired by the mythical Greek figure who dared to fly too close to the sun. The discovery of Icarus has opened an exciting new window into the early universe. It shows that by combining the colossal gravitational lensing effect of massive galaxy clusters with the more delicate microlensing from smaller objects inside those clusters, astronomers can not only study ancient stars but also test theories about dark matter and catch glimpses of rare, high-energy events in galaxies that existed when the universe was still young. When Hubble spotted it, it was the farthest star ever observed. The light we see from Icarus began its journey when the universe was only about 30% of its current age. At that moment, it was at least 100 times farther away than the nearest star to us. And yet, we can still go farther, into distances so great they challenge the very limits of our understanding. Far away in the constellation of Cetus, there lies a star with a name that sounds like it was pulled straight from a fantasy tale, Arendelle. Officially called WHL 0137LS, it was spotted in the year 2022 by the Hubble Space Telescope. This is not just any star. It is the farthest and earliest star ever seen by human eyes, its light travelling for nearly 13 billion years before finally reaching us. Yet, because the universe has been stretching and expanding all this time, Arendelle's true location today is a staggering 28 billion light-years away. Before Arendelle's discovery, the record was held by another distant star known as Max J, 1149 lensed star 1, nicknamed Icarus. Found by Hubble in the year 2018, Icarus sat at a comoving distance of about 14.4 billion light-years. Arendelle, however, shattered that record. The only reason we can see stars like Arendelle at such impossible distances is because of a cosmic trick called gravitational lensing. In simple terms, massive galaxy clusters between us and the star bend and magnify its light, acting like a giant natural telescope. In Arendelle's case, the galaxy cluster WHL 013708 sits perfectly in the way, focusing the star's ancient light toward Earth. Simulations suggest its brightness was boosted by anywhere between 1,000 and an astonishing 40,000 times. Hubble's camera first caught Arendelle's light on 4 separate occasions: the 7th of June 2016, the 17th of July 2016, the 4th of November 2019, and the 27th of November 2019. The official announcement came later, on the 30th of March 2022. The name Arendelle comes from Old English, meaning morning star or rising light. But there's also a wink to literature here. Arendelle is a heroic half-elven character in J.R.R. Tolkien's The Silmarillion, who sails the heavens carrying a brilliant jewel that shines like a star. NASA astronomer Michelle Thaler confirmed the Tolkien reference was very much intentional. Arendelle's home galaxy, WHL 0137ZD1, got its own nickname, Sunrise Arc, because the gravitational lensing stretched its light into a graceful glowing crescent. Both Hubble and the James Webb Space Telescope have continued watching Arendelle, hoping to learn more. Webb, with its greater sensitivity, can study the star's light in detail to see whether it is a lone star or perhaps 2 stars in orbit. By looking at its spectrum, scientists can also detect if the star contains any elements heavier than hydrogen and helium. On the 30th of July 2022, Webb captured its first image of Arendelle. A little over a year later, on the 8th of August 2023, both Hubble and Webb recorded its colours. Webb's observations revealed that Arendelle is a massive blue-white B-type star, more than twice as hot as our Sun, and about 1 million times brighter. There are even hints that it might have a cooler, redder companion star. However, in early 2025, a new scientific paper suggested the magnification might actually be only 43 to 67 times, far less than the original estimate, which could mean Arendelle may not be a single star after all. The light we see from Arendelle began its journey just 900 million years after the Big Bang. Its redshift, a measure of how much the light has been stretched by the expansion of space, is 6.2, meaning that it took 12.9 billion years for that light to reach us. Today, the universe has placed Arendelle at an unimaginable 28 billion light-years away from Earth. If it truly is a single star, its surface temperature lies somewhere between 13,000 and 16,000 Kelvin, and it blazes with a luminosity of between 600 and 31,000 and nearly 4 million times that of our Sun. But there's a puzzle. The way its light behaves suggests it might actually be 2 stars, one a hot blue star at around 34,000 Kelvin, and the other cooler at about 9,000 Kelvin. The data is still too limited to say for sure, and if there are indeed 2 stars, each might be magnified differently, making the mystery even deeper. Far beyond the cold, stormy blue world of Neptune lies a vast and shadowy realm, a cosmic wilderness where the frozen relics of our solar system's birth have drifted undisturbed for billions of years. Here, in the frigid blackness, these ancient fragments are perfectly preserved by the deep freeze of space, untouched since the earliest days of the Sun and planets. To reach this lonely and mysterious frontier from Earth, we would have to travel outward step by step. First, we would pass the rocky worlds, Mercury, Venus, Earth, and Mars. Beyond Mars, we would sail past the swirling clouds of Jupiter, the largest planet of them all, and then past Saturn with its majestic rings. Further still, we would leave behind the pale blue giants Uranus and Neptune. Only then, after this long voyage, would we arrive at our destination, the Kuiper Belt, a gigantic ring of icy debris that circles the Sun like a frozen halo. But the Kuiper Belt is not simply a distant scattering of frozen rocks. It is a time capsule, a vault of untouched material from more than 4.5 billion years ago, the very building blocks from which our planets once formed. It holds dwarf planets, strange icy worlds, and mysterious objects that have puzzled astronomers for decades. Before we knew for certain that the Kuiper Belt existed, scientists had long suspected there was something out there. For many years, Pluto, everyone's favourite dwarf planet, was thought to be alone in the darkness beyond Neptune, but its tiny size and strange tilted orbit hinted that it might not be a lonely wanderer at all. In the year 1951, the Dutch-American astronomer Gerard Kuiper suggested that a belt of icy worlds might exist just beyond Neptune's orbit. The idea remained only a theory for decades, Because no telescope at the time was powerful enough to spot such distant, faint objects. That changed in the year 1992 when astronomers David Jewett and Jane Liu discovered the first confirmed Kuiper Belt object, or KBO, which they named 1992 QB1. Pluto had been discovered much earlier, in 1930, and its largest moon, Charon, was found in 1978. Yet, only after the discovery of 1992 QB1 did scientists realise that Pluto and Charon were actually part of a much larger icy population. Since that historic find, thousands more Kuiper Belt objects have been identified, revealing a vast hidden frontier beyond Neptune. To picture the Kuiper Belt's place in our solar system, imagine we are travelling in a spaceship starting from the Sun and heading outward. First, we pass the inner rocky worlds, Mercury, Venus, Earth, and Mars. Between Mars and Jupiter lies the asteroid belt, a thin ring of rocky fragments left over from planet formation. This asteroid belt sits about 2.2 to 3.2 astronomical units from the Sun, with 1 astronomical unit being the distance from the Earth to the Sun. Most known asteroids live here, from the giant Vesta, about 525 kilometres across, almost the distance from London to Belfast, to tiny space rocks only a few dozen kilometres wide. Yet, despite its size, the combined mass of all the asteroids in this belt is only about 3% of the mass of our Moon. Beyond the asteroid belt rise the great outer planets, Jupiter, Saturn, Uranus and Neptune, massive worlds that dominate the outer solar system. Then, at 30 astronomical units from the Sun, we finally cross into the Kuiper Belt. This frozen realm stretches from 30 to 50 astronomical units and is home to countless treasures. Dwarf planets such as Pluto, Haumea, Eris, and Makemake, along with an uncountable number of smaller icy bodies. Like the asteroid belt, the Kuiper Belt is made of ancient debris from the earliest days of the solar system. Scientists believe these objects are some of the oldest surviving pieces of the swirling cloud of gas and dust, the solar nebula, that once formed the Sun and planets. Long ago, these frozen fragments might have merged into another planet, but Neptune's powerful gravity stirred up their orbits and kept them from coming together. Unlike the asteroid belt, which is made mostly of rock, the Kuiper Belt is rich in frozen methane, ammonia, and water ice, forming a thick donut-shaped ring of icy rubble. It contains hundreds of thousands of large icy bodies, more than 100 kilometers across, over 1 trillion comets, and countless smaller pieces of debris. The distances between these objects are staggering, on average between 0.02 and 0.1 astronomical unit apart, which is roughly 10 million kilometers. Out here, in the dim outer reaches of the solar system, these icy worlds drift almost silently, holding vital clues about the birth of planets, the history of comets, and perhaps even the origins of life itself. And the Kuiper Belt is not the end of the story. Beyond its main region lies the scattered disk, where icy bodies are flung onto stretched and tilted orbits, some reaching nearly 1,000 astronomical units from the Sun. A few objects wander even farther still, on paths that may take them toward the most distant structure of all, the Oort Cloud, the farthest frontier of our Sun's domain. Far beyond the planets we know, past the blazing Sun, the rocky inner worlds, and the giant planets made of gas and ice, there lies one of the most mysterious structures in our cosmic neighbourhood, the Oort Cloud. This colossal sphere of icy debris surrounds our entire solar system like a ghostly shell. It is so unimaginably far away that even the most powerful telescopes ever built cannot see it directly. Astronomers believe the Oort Cloud begins roughly 2,000 astronomical units from the Sun, and may stretch all the way to 100,000 astronomical units, almost halfway to the nearest stars. To give some perspective, 1 astronomical unit is the distance from Earth to the Sun. That means the Oort Cloud begins more than 2,000 times farther away than Earth and the Sun, and at its edge it is 50 times farther than Pluto. Closer in, but still beyond Neptune, lies another great realm, the Kuiper Belt. This vast, icy region is thousands of times nearer to the Sun than the centre of the Oort Cloud. The Kuiper Belt is shaped like a giant flattened ring, or donut, while the Oort Cloud is thought to be a perfect sphere, like a gigantic bubble of frozen fragments drifting in space. Despite their differences in shape and distance, these two regions share something in common: They are the birthplaces of comets. The Oort Cloud sends us many of the so-called long-period comets, which take thousands or even millions of years to complete an orbit around the Sun. The Kuiper Belt, on the other hand, is home to short-period comets, which swing around the Sun in less than 200 years. The Kuiper Belt that exists today is only a shadow of its former self. In the early days of the solar system, astronomers believe it held between 7 and 10 times the mass of Earth. But as the 4 giant planets, Jupiter, Saturn, Uranus and Neptune, shifted their orbits, their immense gravity flung most of that material into space, or toward the Oort Cloud. Now, the Kuiper Belt contains only about 10% of Earth's mass. Even now, the Kuiper Belt is slowly eroding. From time to time, icy bodies collide, shattering into smaller pieces. Some fragments become dust that the solar wind blows out of the solar system. Sometimes Neptune's gravity nudges objects onto a new path, sending them toward the Sun to become short-period comets. As these comets draw close to the Sun, its heat causes their icy surfaces to vaporize, creating the spectacular glowing tails we can see from Earth. Some of the most famous comets we know come from the Kuiper Belt or its nearby scattered disk. One example is Halley's Comet, which has an average orbital period of 76 years. Another is Comet Shoemaker-Levy 9, which famously broke apart and slammed into Jupiter in the year 1994, the first collision between 2 solar system bodies ever witnessed by humans. Jupiter, of course, survived the blow, but the scars of the impact were visible from Earth for weeks. Not long ago, the news carried reports of a near-Earth asteroid named 2024 Y4. While there is an extremely tiny chance of it hitting our moon, and an even smaller chance of striking Earth, astronomers assure us that short-period comets from the Kuiper Belt pose no threat to us for at least the next 100 years. The Oort Cloud remains beyond our reach, but the Kuiper Belt is a different story. While most of what we know about it comes from Earth-based telescopes and the Hubble Space Telescope, only one spacecraft has ever been there: NASA's New Horizons. In 2015, New Horizons made history with its breathtaking flyby of Pluto, capturing the most detailed images ever taken of the dwarf planet and its moons, but the mission did not end there. On New Year's Day of 2019, New Horizons flew past a small Kuiper Belt object called 2014 MU69, later named Arakoth, a word meaning sky in the Powhatan and Algonquian languages. This was the most distant flyby in the history of space exploration, taking place 1.5 billion kilometers beyond Pluto. The spacecraft came within about 3,500 kilometers of Arakoth's surface. Arakoth turned out to be unlike anything scientists had seen before, a contact binary made of 2 icy lobes joined together into one body. It looks like a flattened snowman, about 35 kilometers long, 20 kilometers wide, and 10 kilometers thick. Though it is tiny compared to planets, Arakoth carries clues about how the building blocks of planets, called planetesimals, formed in the early solar system. Before this encounter, 2 main theories existed: hierarchical accretion, which suggested that small objects smashed together at high speeds to form bigger ones, and local cloud collapse, which proposed that nearby material slowly came together under its own gravity. The smooth surface of Arakoth and the absence of violent collision marks strongly support the second theory. In the words of planetary scientist Alan Stern, the New Horizons leader, the evidence decisively solved a multi-decade debate about how planetesimals form. And of course, there is Pluto, the Kuiper Belt's most famous resident. New Horizons revealed its stunning heart-shaped region, called Tombor Regio, after Pluto's discoverer Clyde Tombor. The western half of this heart is Sputnik Planitia, a vast glacier made of nitrogen ice that stretches about 1,000 kilometers across and sinks roughly 4 kilometers deep, making it the largest known glacier in the solar system. Data from New Horizons showed that Pluto is far more complex than scientists once thought, with hints that a hidden ocean of water ice might exist beneath its frozen surface. That icy heart may not just be a charming shape, it might be the clue to one of Pluto's greatest secrets. A recent scientific investigation, led by astrophysicist Harry Valentine from the University of Ben, has offered an intriguing new explanation for one of Pluto's most famous features, its giant pale heart. For years, people wondered why this heart-shaped mark appeared on Pluto's icy surface. Now researchers believe that the answer might be a slow but powerful cosmic collision. According to Valentine's team, the western side of Pluto's heart may have been formed when a large object slammed into the dwarf planet at a low speed and from a slanted angle, not head-on. Imagine tossing a water balloon across a dry sidewalk, the way you might skip a flat stone across a calm pond. Instead of bursting in a neat circle, the balloon scrapes the ground, bursts, and leaves an elongated splash of water. In much the same way, this angled impact could have left an enormous splatter pattern on Pluto's surface, shaping the left half of its famous heart. But Pluto wasn't the only world to amaze scientists during NASA's historic New Horizons mission. The spacecraft also captured breathtaking close-up images of Charon, Pluto's largest moon. One of Charon's most striking features is its immense equatorial tectonic belt, a rugged scar stretching across its middle. This gigantic geological feature hints at a dramatic past. It may be evidence of a long-vanished ocean of liquid water ice hidden beneath Charon's crust billions of years ago. The story of exploration does not end here. New Horizons is expected to leave the Kuiper Belt, that vast ring of icy worlds beyond Neptune, sometime between the years 2028 and 2029. As of now, NASA has no confirmed destination for another close flyby, but it remains possible that a new, intriguing target will be found. In the meantime, powerful tools like the James Webb Space Telescope could help scientists study the chemistry and surface features of Kuiper Belt objects from afar. And perhaps, in the distant future, humanity might send a robotic probe to land on one of these mysterious frozen bodies, or even bring back a sample to Earth. This far-off region of space remains a vast frozen frontier full of secrets. As technology improves, future missions will journey deeper into the Kuiper Belt, unveiling its ancient mysteries one icy world at a time. Who knows what strange and wonderful discoveries still await us in this distant wilderness at the edge of our solar system. In the year 1977, two daring explorers set out on what might be one of the greatest adventures in the history of space travel. These were not astronauts in shiny suits, but two robotic pioneers, Voyager 1 and Voyager 2, each carrying humanity's curiosity far beyond our home. Their mission was bold, to unravel the cosmic mysteries of our solar system and discover more about our place in the vast universe. They did far more than anyone expected. They sent back some of the very first and clearest pictures we had ever seen of the giant planets in the outer solar system. Colossal worlds like Jupiter, Saturn, Uranus, and Neptune, along with their strange and beautiful moons. And even now, after more than 47 years and over 24 billion kilometers of travel, they are still whispering to us from the dark, cold reaches of interstellar space. Voyager 1 and Voyager 2 are not just collections of metal, wires, and instruments. They are symbols of what humanity can achieve at its very best. Curious, fearless, ambitious, and resilient. They did not merely take breathtaking close-up portraits of the gas giants, they captured the hearts and imaginations of millions back on Earth. These are the farthest travelled human-made objects in history, true trailblazers venturing into territory where no one and nothing has gone before. Their journey takes them far beyond the reach of any rescue, into a lonely darkness where no other machine or human has ever wandered. As Edward Stone, the Voyager mission's project scientist, once reflected, "When I look back, I realise how little we actually knew about the solar system before Voyager. Time after time we discovered things we did not even know were there to be discovered. It is a curious twist of fate that the most important discoveries at the very edge of our solar system are not being made by shiny new technology, but by these aging explorers from the 1970s. Their computers have less memory than the chip inside a modern car key fob. They still use 8-track magnetic tape to store data, technology older than many of the people reading this. That is the strange reality of deep space exploration. The vast distances and decades-long travel times mean that by the time a spacecraft arrives at its destination, its technology is considered ancient back on Earth. When they launched in 1977, Voyager 1 and Voyager 2 were never intended to reach interstellar space. They were designed for a 5-year mission to study Jupiter, Saturn, and their largest moons. This was only possible thanks to a rare planetary alignment that occurs just once every 176 years, an alignment that last happened when Napoleon Bonaparte ruled France. This cosmic lineup allowed each probe to slingshot from planet to planet, using the immense gravity of each world to boost its speed without burning precious fuel. After their work at Jupiter and Saturn was done, Voyager 2's mission was extended to include visits to Uranus and Neptune, making it the only spacecraft to have ever visited those two ice giants. Once these flybys were complete, NASA set them on an even grander adventure, the Voyager Interstellar mission. This final stage would carry them to the farthest edges of the Sun's influence, into mysterious regions like the termination shock and the turbulent heliosheath, before finally breaking through the heliopause into the true emptiness of interstellar space. How did they achieve so much more than originally planned? The secret lay in the brilliant, forward-thinking design choices made by NASA's engineers. Each Voyager carries 11 scientific instruments, many with backup systems that can be switched on if the primary ones fail. For navigation, the probes have gyroscopes for stability, special reference sensors, and 16 hydrazine thrusters, 8 of which are backups. This redundancy proved invaluable. After 37 years in space, Voyager 2's main thrusters failed, and its backups, untouched for 4 decades, were activated. Incredibly, they worked perfectly. Powering each probe is a radioisotope thermoelectric generator, or RTG, which turns the heat from the slow decay of plutonium-238 into electricity. At launch, each generator produced about 157 watts, enough to power a small laptop and charge a phone, and while the output decreases by half roughly every 87 years, it was enough to keep the Voyagers alive well into the 21st century. NASA expects they will still be able to send back data until around the year 2025. The Voyager's computers, though primitive by today's standards, were cutting edge in their time. Their wide-angle and narrow-angle cameras are controlled by an onboard command system capable of fault detection and automatic corrections. Every feature was built to last because once launched, there would be no way to fix or upgrade them. And so, with their ancient but trusty technology, these two golden messengers continue their long voyage into the dark, carrying not only humanity's instruments, but also humanity's hopes. One of the greatest secrets behind the Voyager mission's success lay in their computers. Each probe carried a special brain called the Attitude and Articulation Control Subsystem. And no, despite its name, it wasn't there to scold the spacecraft for having a bad attitude. In space talk, attitude simply means the way the spacecraft is positioned in relation to Earth. Without this precise orientation, the Voyager probes would not have been able to point their large, high-gain antennas toward our planet, and they would have been unable to send or receive even the faintest signals from NASA's deep space network. This was absolutely vital because the probe's radio transmitters were incredibly weak, putting out about the same power as the tiny light bulb inside your refrigerator. At such mind-boggling distances from Earth, those signals fade into whispers so faint that only the most sensitive antennas on Earth can detect them. For the Voyagers to talk to their team, and for the team to talk back, the probe's antennas had to be aimed with pinpoint accuracy at our planet, and the deep space network also had to know exactly where in the heavens the probes were. Without this careful alignment, they would have been as hopelessly lost as a single needle, hidden somewhere inside a haystack stretching 287 billion kilometers across. Each Voyager carried a 3.7-meter wide antenna for sending information in real time, and an 8-track digital tape recorder for saving data to transmit later. This tape recorder could store 536 megabits of information, enough to hold about 100 photographs. At the time, this was a huge leap forward compared to the earlier Pioneer probes, which had no ability to store data on board. Of course, by today's standards, it's tiny. Your smartphone probably holds thousands of times more information. But what the Voyagers lacked in storage, they made up for in toughness. The company that built their tape recorders, Odetics, claimed that each unit could run through more than 4,000 kilometers of tape without showing any wear. These devices were designed to survive the harshest and most unforgiving conditions in space, extremes that had never been tested before, and they proved themselves. The Voyager's tape recorders worked flawlessly, without losing data or breaking down, until they were finally shut down to save power. Not bad for machines that were already 12 years older than the World Wide Web when that moment came. Durability was a top priority during the Voyager's planning. Space is full of unknown dangers, and to reach Jupiter, both spacecraft would have to pass through the asteroid belt. In the early days, scientists feared this belt might be so packed with rocks and debris that any spacecraft trying to cross it would be torn to pieces. But when Pioneers 10 and 11 successfully passed through, Voyager's team gained the confidence to try the same route. Failure would have meant the mission ending before it even reached its first destination. Thankfully, both Voyagers sailed through the asteroid belt unharmed, teaching us that this region is, in fact, mostly vast empty space. Even with these victories and better-than-expected performance, another challenge loomed: the bitter cold of deep space. NASA had fitted the probes with heaters to keep their systems warm, but as the power supply slowly weakened over the decades, some heaters had to be switched off. When the heater for one of Voyager's cosmic ray detectors was turned off just 2 years ago, its temperature plunged by 70 degrees Celsius. Everyone assumed the instrument would soon fail. After all, you can't send a repair crew 23 billion kilometers away. But astonishingly, it kept running perfectly. The fact that these probes have been working for 45 years is a shining tribute to their engineering and endurance. So, with all this technology in place, what did they see? To answer that, let's rewind to the very start of their journey. On the 20th of August, 1977, NASA launched Voyager 2 from Cape Canaveral, Florida. Its twin, Voyager 1, lifted off exactly 2 weeks later, on the 5th of September. Even though both were headed for Jupiter, Voyager 1's route was shorter and faster, so launching it second made perfect sense. It soon overtook Voyager 2 on the 15th of December 1977 and became the first to leave the asteroid belt. Together, this daring pair of explorers was about to capture a breathtaking gallery of photographs unlike anything the world had ever seen. Just 13 days after launch, Voyager 1 sent back its very first picture. Taken from a distance of 11.6 million kilometers, it showed our planet and its lone moon hanging together in the blackness of space. It was a sentimental starting point for the mission, reminiscent of the famous Earthrise photograph taken by the Apollo 11 crew just 8 years earlier. Our fragile blue home glows softly against the endless dark, a hauntingly beautiful image, especially when you consider how far the probe had already travelled and how much more it would see in the decades to come. From there, the wait began. It would take almost 2 years for Voyager 1 to reach its first destination, Jupiter. Not bad, considering the gas giant lies 714 million kilometers from Earth. Voyager 1 arrived first on the 5th of March, 1979, cruising at 17 kilometers per second, about 2 kilometers per second faster than Voyager 2, which, despite launching first, reached Jupiter 4 months later, on the 9th of July 1979. Voyager 1 was not the first spacecraft to meet Jupiter. Pioneer 10 had done so 7 years earlier, in 1972. But while Pioneer gave us valuable science, it didn't capture the public's imagination in the same way. Voyager's images did. The photos were so sharp and vibrant that they seemed almost unreal, as if they were paintings rather than actual photographs. In one stunning image, Jupiter's swirling clouds dominate the frame, with 2 of its moons visible, Io, glowing yellowish on the left, and Europa, pale and beige on the right. Voyager 1 even documented its approach to Jupiter in motion. By taking photographs every 10 hours, exactly 1 Jupiter day, it captured the planet from the same point in its rotation each time. These 66 images were stitched together into a mesmerizing time-lapse video, showing the spacecraft's journey from the 6th of January to the 3rd of February, 1979, as it closed the gap over a span of 27 million kilometers. One of the very first things that left scientists absolutely astonished was the atmosphere of Jupiter. They had expected to find the planet's air flowing in neat east-west and west-east winds, each confined to its own atmospheric zone like well-behaved stripes. But the reality was far more chaotic and mesmerizing. What the Voyager spacecraft revealed was a world of roaring turbulence, towering plumes, and swirling rotational patterns so vivid that they almost seemed alive in the images. You could instantly tell that Jupiter's atmosphere is one of the most dynamic and restless environments in the solar system. Scientists had long suspected that Jupiter's most famous feature, the colossal Great Red Spot, was a vast counterclockwise spinning storm. Voyager's instruments confirmed this suspicion beyond doubt, but that was only the beginning. The spacecraft also revealed that the Great Red Spot was far from alone. Jupiter's skies were teeming with other whirling tempests. One example was a large white storm swirling just beneath the Great Red Spot, an unexpected find that hinted at countless other hidden tempests. It turns out Jupiter's atmosphere is absolutely littered with these monster storms, and until Voyager's visit, we had no idea they even existed. When most people hear the word rings, they think of Saturn. But data from earlier missions like Pioneer had hinted that Jupiter might have its own set of rings too. Voyager not only confirmed their existence, it became the first spacecraft to actually photograph them. The images showed 4 delicate, faint Jovian rings, captured as Voyager was departing the planet. In the photograph, the rings appear as a glowing orange line stretching from the planet's edge, delicate yet majestic. Before leaving Jupiter's realm, Voyager delivered what was perhaps its most jaw-dropping revelation: the astonishing volcanic activity on its moon Io. Before this, planetary geologists were convinced Io would be much like our moon, scarred with countless craters from ancient impacts. And indeed, Voyager did spot circular features on Io's surface, but they weren't craters. They were something far more dramatic: volcanic calderas and lava lakes. The spacecraft revealed that Io had lava flows less than 1 million years old, which in planetary terms is incredibly recent. In fact, Io turned out to be the most geologically active world in the entire solar system. The surprise was unimaginable. Scientists had expected a frozen, lifeless moon, but instead found a hellish landscape bursting with activity. Some of the volcanoes erupted with such force that blue-hued plumes of material and gas were launched 100 kilometers into space. These eruptions happened relentlessly, sometimes every few hours, providing Voyager with several breathtaking snapshots of a truly alien world. Just beyond Io lies Europa, a moon that could not be more different. Voyager 1 was the first to show that Europa's surface is covered in strange scratch-like markings, long dark lines that scientists believe are fractures in a thick sheet of surface ice. The spacecraft's data also hinted at something even more tantalizing. Beneath Europa's icy crust, there might be a hidden, swirling ocean. Today, we believe that this subsurface ocean could potentially harbour the conditions necessary for life. At present, we know of 95 moons orbiting Jupiter. But before the year 1979, astronomers had only identified 13. Voyager's sharp-eyed cameras discovered 3 more: Thebe, Metis and Adrastea, raising the total count at the time to 16. Unfortunately, the newly found moons were too faint for Voyager to capture in detail, but later observations have given us clearer images. After 21 months of travel through space, Voyager 1 reached Saturn in November of 1980, with its twin Voyager 2, arriving 9 months later in August of 1981. And of course, when you think of Saturn, you think of rings. Before Voyager's flyby, scientists believed Saturn had only 5 major rings, but the spacecraft revealed that each of those rings is actually made up of hundreds of narrow ringlets, like threads woven into an intricate cosmic tapestry. Voyager also discovered a brand new ring, now called the G ring, and provided our first close look at the F ring, first detected by Pioneer 11 in 1979. To everyone's amazement, the F ring was not a smooth, single structure. It was kinked, braided, and made up of multiple strands. Voyager even spotted 2 tiny shepherd moons, Prometheus and Pandora, whose gravity helps keep the F-ring's material from drifting away. Another bizarre discovery came from Saturn's B rings, which appeared to contain ghostly, spoke-like patterns, broad, radial streaks that seemed to float across the ring system. Up until 1980, scientists thought the shapes and movements of Saturn's rings were controlled entirely by gravity. But these mysterious spokes did not follow the rules of orbital mechanics. The leading theory now suggests that they are caused by electrostatic forces, with tiny dust grains being charged and lifted away from the ring surface. Yet not all of Voyager's findings were cheerful. The data suggested that Saturn's rings are slowly disappearing, with gravity pulling icy particles into the planet as a fine, dusty rain. According to NASA's calculations, the rings could vanish entirely in about 300 million years, a mere blink in cosmic time. The mysteries uncovered by Voyager were so compelling that, in the 1990s, NASA launched a dedicated mission to Saturn, the Cassini probe. Launched in 1997, Cassini spent 13 years orbiting the ringed planet, revealing even more about its complex system. Voyager also expanded our knowledge of Saturn's moons. Before its arrival, 14 were known, but Voyager found 3 more, bringing the total to 17. Among the most intriguing were Titan and Enceladus. Pioneer 11 had been the first to photograph Titan, but Voyager revealed that this enormous moon possesses a thick, nitrogen-rich atmosphere, the only moon known to have such an atmosphere outside Earth. Enceladus, on the other hand, turned out to be a small but astonishingly active world. From a great distance, Voyager photographed a faint icy plume rising from its surface, an eruption of water vapour. This tiny moon ejects about 300 kilograms of vapour every second, shooting it up to 10,000 kilometers high, 20 times its own diameter. These plumes create a donut-shaped cloud that feeds one of Saturn's icy rings. Although Voyager's data suggested this activity, it would take Cassini decades later to confirm it in spectacular detail. Further geological evidence and high-resolution images have revealed something unexpected about the icy moon Enceladus. Its surface is not uniform at all. Instead, it is a fascinating mix of ancient and young terrains. The left side, smooth and relatively unscarred, is clearly the newer region. The right side, however, is covered in a dense field of impact craters, marking it as much older. This contrast shows that Enceladus is far more geologically active than scientists once believed. Before these findings, no one thought this little moon had such a restless and changing surface. But before we can head toward the strange tilted world of Uranus, we must bid farewell to Voyager 1. After its historic flyby of Saturn's majestic rings and the haze-covered moon Titan, the probe's path was bent upward and away from the flat plane in which most planets orbit, a cosmic exit ramp that sent it toward interstellar space. It would take another 32 years before it finally crossed that boundary, but that is a story for later. Its twin, Voyager 2, took a different route. It swung around Saturn in a precise gravitational slingshot maneuver, using the planet's immense pull to propel it onward toward Uranus and then Neptune. These would become the very first, and still the only, close encounters humanity has ever had with these distant ice giants. 5 years after arriving at Saturn, Voyager 2 reached Uranus in January of the year 1986. At its closest approach, the spacecraft passed within 81,500 kilometers of the planet's upper cloud tops. What it saw was surprising. Unlike Jupiter and Saturn, Uranus showed almost no obvious cloud formations. Instead, it displayed a calm, pale, and nearly featureless atmosphere, challenging scientists' ideas about how gas giant atmospheres work. In a false color image, subtle differences could be seen between Uranus's polar regions, which are themselves tilted on a wild 98-degree axis. But there was another tilt that left scientists stunned: the planet's magnetic field. Before Voyager 2's visit, no one even knew if Uranus had a magnetic field. The probe revealed that not only did it have one, but it was tilted an incredible 59 degrees away from the planet's rotational axis. On Earth, the difference between our magnetic and rotational poles is only about 12 degrees. This extreme misalignment shattered previous models of how planetary magnetic fields are supposed to work. Because of this tilt, Uranus's magnetosphere, the bubble of space shaped by its magnetic field, wobbles and lurches as the planet spins, almost like a poorly thrown American football. Scientists still cannot fully simulate how this works, but Voyager's data gave them their first real clues. The spacecraft also provided the first close-up images of Uranus's dark and dusty rings, as well as the discovery of 2 new rings and 2 small shepherd moons that help keep one of those rings in place. In a photo taken from 4 million kilometers away on the 21st of January 1986, the outermost ring can be seen faintly glowing against the blackness. Voyager 2 also greatly expanded our knowledge of Uranus's moons. Before its arrival, astronomers knew of only 5. The probe sent back the first ever close-up images of these original moons, while also discovering 11 new ones, increasing the total to 16. Today, we know that Uranus has 27 moons in all. The 5 original moons are Oberon, Umbriel, Titania, Ariel, and Miranda. Oberon and Umbriel photographed on the 24th of January 1986, are dark, heavily cratered, and appear geologically inactive. Titania, the fourth farthest of the five, is marked by enormous faults and deep canyons, hinting at past tectonic activity. Ariel is the brightest and possibly the youngest looking of them all. A close photo taken from just 129,000 kilometers away revealed a surface scarred by fault valleys and streaked with icy flows, clear signs of a dramatic geological past. But the greatest surprise was Miranda, the innermost of the large moons, second only to the tiny moon Puck in proximity to Uranus. Voyager 2 flew past Miranda on the 4th of January 1986, at a distance of only 30,000 kilometers. What it saw was astonishing, a patchwork world shaped by a chaotic history. Huge canyon-like troughs plunge 20 kilometers deep, oval, racetrack-shaped markings stretch across its surface like cosmic fingerprints. There are bright and dark regions, smooth and cratered areas, and bizarre chevron patterns suggesting that Miranda's crust had been ripped apart and then reassembled, piece by piece. 3 weeks later, on the 25th of January, Voyager 2 took a final farewell shot of Uranus from 1 million kilometers away before heading toward its last planetary target, Neptune. After 3 more years of travel, racing through the void at 54,000 kilometers per hour, Voyager 2 finally arrived. On the 25th of August 1989, just over 12 years after leaving Earth, it came within 5,000 kilometers of Neptune's North Pole, the closest any spacecraft has ever come to the blue giant. It revealed that Neptune's atmosphere is mostly hydrogen, with enough methane to give it its striking blue colour. The probe also measured astonishing winds, the fastest in the entire solar system, with speeds near the equator reaching almost 1,100 kilometers per hour. Neptune had one more surprise in store, a revelation that showed just how wild, restless, and downright ferocious its weather systems could be. Among the planet's many marvels, scientists spotted a gigantic storm that they fittingly named the Great Dark Spot. This swirling behemoth rotated in a counterclockwise direction, much like Jupiter's famous Great Red Spot, but it had a far darker and more mysterious appearance. What was even more astonishing was its sheer power. The winds raging inside it reached staggering speeds of up to 2,400 kilometers per hour, making them the fastest winds ever recorded anywhere in the entire solar system. NASA analyst Ken Bollinger, reflecting on the Voyager 2 discoveries back in the year 1989, summed up the excitement perfectly. Every day what you see is brand new. Nobody's ever seen it. It's just an incredible feeling. There's changes going on constantly on Neptune that happen very, very fast. And Neptune's surprises didn't end there. For the first time in history, Voyager 2 managed to capture images of the planet's elusive rings. Up until the year 1986, astronomers suspected Neptune might have a ring system, but no one could be completely sure. When the truth was finally revealed, it came with a twist. Rather than being solid, continuous bands like Saturn's, Neptune's rings were strange, dusty, and incomplete, existing in the form of several partial arcs. These arcs puzzled scientists, raising big questions about how they formed and how they managed to remain stable instead of simply dispersing into space. Of course, no visit to Neptune would be complete without paying a call to its largest moon, Triton, a frozen and otherworldly realm. Triton holds the record as the coldest known planetary body in the solar system, yet it is far from lifeless. Voyager 2 revealed a cracked and fractured landscape dotted with erupting geysers that shot plumes into the thin atmosphere. Over its southern pole lay a strange pinkish nitrogen ice cap, giving the moon a ghostly beauty. Scientists even spotted dark streaks on the surface, possibly the telltale signs of cryovolcanoes, volcanoes that erupt ice instead of lava. As if that were not enough, Voyager 2 discovered 6 new moons orbiting Neptune during its flyby. Then, with its mission at Neptune complete, the spacecraft turned its camera around for one final farewell snapshot of Neptune and Triton before its trajectory, bent by the planet's gravity, sent it diving downward out of the ecliptic plane, the flat, disk-like region in which most planets orbit the Sun. From there, it set course for the great unknown of interstellar space, just as its twin, Voyager 1, had done 9 years earlier. Speaking of Voyager 1, By the year 1980, only 1 year after Voyager 2's close encounter with Neptune, it was already about 6 billion kilometers from Earth. To save precious power for the long and lonely journey into interstellar space, mission planners intended to shut off its cameras forever. But famed astronomer Carl Sagan had another idea. Why not turn the camera around and take one last look at home? And so, on the 14th of February 1990, Voyager 1 captured the most distant selfie in human history, the legendary pale blue dot photograph. From 6 billion kilometers away, Earth appeared as nothing more than a faint speck, a single pixel suspended in the deep black of space caught in a shaft of sunlight. Carl Sagan's poetic words about that tiny dot still echo through time. Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. That message is just as powerful today as it was 33 years ago. But what happened after that? What awaited the Voyagers in the vast wilderness between the stars? In the year 1981, Voyager 1 broke free from the ecliptic, veering 35 degrees north of Earth's orbital plane. Voyager 2 would later take a different route, diving 48 degrees south. But these course changes were just the beginning of a much longer odyssey. To truly enter interstellar space, the probes would need to pass through several invisible but dramatic boundaries. First came the termination shock, the region where the sun's supersonic solar wind slows down abruptly, colliding with the opposing flow of interstellar particles. Beyond that lay the heliosheath, where the solar wind becomes hotter and denser as it piles up. Finally, the Voyagers would reach the heliopause, the ultimate frontier, marking the boundary between the sun's protective bubble, the heliosphere, and the space between the stars. Even beyond that, the solar system still isn't truly over. Astronomers estimate it will take Voyager 1 another 300 years just to reach the inner edge of the Oort Cloud, a vast bubble of icy objects that surrounds the solar system, and another 30,000 years to finally leave it behind entirely. While travelling through the heliosheath, the Voyagers made a discovery that forced scientists to rethink their understanding of this region. The sun's magnetic field flips direction between its northern and southern hemispheres, creating a vast, wavy surface called the heliospheric current sheet, a little like ripples spreading outward after a stone is dropped into a pond. But when this sheet reaches the termination shock, it gets compressed, as if those ripples were suddenly hitting the edge of a pool. Voyager's instruments revealed that in this compressed state, the ripples actually break up into huge magnetic bubbles, meaning the outer boundary of the heliosheath is far messier and more turbulent than anyone imagined. Rather than a smooth, clearly defined frontier, it is a chaotic and ever-changing magnetic sea. This unexpected finding has completely reshaped scientists' models of the sun's outermost reaches, proving once again that the Voyagers, even decades after launch, still have new secrets to share. On the 25th day of July in the year 2012, history was made. The Voyager 1 space probe, a lonely traveller launched decades earlier, became the very first human-made object to cross the invisible frontier of our sun's influence, known as the heliosphere, and step into the vast wilderness of interstellar space. At that moment, it was racing through the darkness at an astonishing speed of about 540 million kilometers every year, the equivalent of 3.6 astronomical units annually. To give perspective, 1 astronomical unit is the distance from the Earth to the Sun, a staggering 150 million kilometers. Voyager 1 made this crossing at roughly 120 astronomical units from the Sun, a distance so far that sunlight takes more than 16 hours to reach it. This, in itself, was a revelation. Until then, nobody knew exactly where the heliopause, the boundary of the Sun's protective bubble, truly lay. Some early predictions had placed it as close as the orbit of Jupiter, while others imagined it far, far beyond. The heliopause is not a solid wall, but rather a region where two cosmic forces meet head-on: the Sun's solar wind and the interstellar medium. It is like the point where two mighty ocean currents crash into each other, churning and pushing in opposite directions. Solar wind is a constant outpouring of charged particles, electrons, protons, and alpha particles, hurled from the Sun's outer atmosphere at tremendous speeds. The interstellar medium, by contrast, is a ghostly blend of charged particles, gases, and fine cosmic dust, the leftovers from the Big Bang and the fiery deaths of ancient stars in supernova explosions. When these two streams collide, they form a shifting zone of balance, the heliopause. When Voyager 1 made its crossing, NASA scientists were thrilled, but also hesitant. The probe's instruments recorded a dramatic surge in plasma density, 80 times higher than what it had measured in the outer Helios heath, and a spike in galactic cosmic rays. This matched the predictions for entering interstellar space. And yet, something odd was missing. The ambient magnetic field did not change. This was puzzling because theoretical models predicted that the orientation of the magnetic field should shift once a spacecraft left the Sun's domain and entered a region influenced by the magnetic forces of other stars. But Voyager 1's magnetometer found no such shift. NASA scientists were so perplexed that they waited almost an entire year before officially announcing the historic achievement. On the 5th of November, in the year 2018, Voyager 2, travelling at the slightly slower pace of 490 million kilometres per year, or 3.3 astronomical units, followed its twin into interstellar space. Its crossing also happened at a distance of 120 astronomical units from the Sun. And, like Voyager 1 6 years earlier, it too found no change in the magnetic field's direction. This was especially surprising because the Sun was at the peak of its 11-year solar cycle, a period when solar winds are at their strongest. According to earlier models, the heliosphere should have expanded during this active phase, meaning Voyager 2 should have crossed at a slightly greater distance than Voyager 1, but it did not. Both probes crossed at exactly the same point, proving that the old models were wrong. The lesson was clear. The heliosphere's edge is far more twisted, irregular, and unpredictable than anyone had imagined. One leading theory suggests that our Sun formed billions of years ago in a violent, superheated, and heavily ionized region, created by one or more nearby supernova explosions. This turbulent magnetic environment may still persist at the heliopause today. If true, the Voyagers might one day detect a change in magnetic orientation, but by then their instruments may have long gone silent, and indeed the signs of aging are already here. In early May of the year 2022, Voyager 1 began behaving oddly. Imagine being a NASA engineer sitting down at your desk ready to check the latest telemetry from your far-flung spacecraft. Signals from Voyager 1 now take 22 hours to reach Earth, like sending letters rather than text messages. But today's data makes no sense. Instead of its usual precise reports on the positions of its thrusters and the exact angle of its enormous 3-meter antenna, Voyager 1 sends back lines of nonsense. Endless strings of zeros or the number 377. These readouts imply that the probe is pointing in impossible directions. Yet, if that were true, you wouldn't be receiving its signal at all. And not only is the signal still coming in, it's just as strong as ever. Stranger still, the science data from Voyager 1's 4 remaining operational instruments, studying cosmic rays, magnetic fields, and the interstellar medium, remains perfectly normal. Over its long journey, the probe has had to shut down 5 of its 11 scientific instruments to save power, while 2 more have failed naturally from wear. Its energy source, 3 radioisotope thermoelectric generators fueled with plutonium oxide, has a half-life of 87 years. After 45 years in space, their output is declining. Experts expect Voyager 1 to fade completely by the mid-2020s, but none of this explains the current problem. The trouble lies in a single subsystem, the ACS, the Attitude and Articulation Control System. This is one of 3 computers aboard Voyager 1, and its job is critical. It keeps the probe's antenna locked on Earth. Without it, the spacecraft could fall silent forever, And yet, somehow, the RIS is sending gibberish, while apparently thinking that nothing is wrong. Voyager 1 has built-in safety protocols that put it into a kind of hibernation mode if something goes seriously wrong. But those have not triggered. It's as if your trusted mail carrier suddenly began speaking in an incomprehensible language every morning, yet still delivered the right packages to your door exactly on time. For NASA's engineers, the mystery was both frustrating and fascinating. The spacecraft was alive, still doing science, still talking to Earth, but its voice was garbled, and it didn't even know it. The question was clear: what exactly was going on, and could they fix it before Voyager 1's final chapter came to an end? In the middle of the year 2022, a single technical glitch might not have looked like a serious problem at first glance. But to those who understood the stakes, it hinted at the possibility that something deeper and far more dangerous might be wrong with other systems on board. If that were true, it could mean the end of the entire mission. By now, Voyager 1 was more than 23,800 million kilometers away from Earth. Any attempt to fix the problem had to be done through slow and careful deduction. Imagine playing a game of 20 questions with a friend on the other side of the solar system, except each question took 22 hours to reach them, and their answer took another 22 hours to get back. That was the reality for NASA's engineers trying to communicate with a distant spacecraft. They began by checking Voyager 1's other systems, and found that everything else seemed perfectly normal. That allowed them to rule out some of the stranger theories. No, this was not aliens playing cosmic pranks. Although NASA had always been open to the idea that the Voyager probes might one day be discovered by alien life, hence the famous golden records attached to them. The records were more of a symbolic hello than a serious attempt at conversation, and even if aliens were out there, this would be a rather odd way to say hi. The laws of physics had not suddenly collapsed either. Voyager 1 had not stumbled into a wormhole that scrambled its navigation, while still somehow keeping its radio signal intact. Since the scientific data being returned looked perfectly normal, the most likely suspect was the AACS, the Attitude and Articulation Control Subsystem, the part of the spacecraft responsible for pointing the antenna at Earth. For 4 months, scientists and engineers tested theory after theory, gently probing the problem and trying to find a solution that would fix it without making things worse. They could switch over to a backup system. Voyager 1 was designed with many redundancies, but that was not without risk. This was not even the first AX computer the spacecraft had used. A previous one had already failed years earlier. Another option was simply to ignore the problem, since the science data was still flowing in, even if some engineering information was garbled. But doing nothing risked overlooking a more serious issue. Eventually they discovered the cause. Out in the harsh, radiation-filled emptiness of interstellar space, something had caused Voyager 1 to start using that older, already broken AACS computer to send its data back to Earth. Because the computer was faulty, the information it sent became scrambled. Thankfully, the fix turned out to be simple. NASA just told Voyager 1 to start using the correct computer again. Once the command reached the spacecraft, the issue was solved, though it still took a couple of months for everything to return completely to normal. But Voyager's troubles were far from over. In November of the year 2023, another computer, the Flight Data Subsystem, developed a similar fault and stopped sending usable science and engineering information back home. It was not until June of the year 2024 that this issue was fully resolved. In July 2023, Voyager 2 had its own heart-stopping moment. A routine set of commands accidentally caused the spacecraft to turn its antenna just 2 degrees away from Earth. That tiny change was enough to completely sever communications across the vast gulf of space. NASA was suddenly deaf and blind to the probe. The only hope was to send a powerful shout from the Deep Space Network facility in Canberra, Australia, commanding Voyager 2 to point back toward home. Then came a tense 37-hour wait for the signal to travel to the spacecraft and for its reply to return. When the response finally arrived, confirming that contact had been restored, it was a moment of pure relief. One day, whether because of a malfunction, a fatal error, or simply running out of power, the Voyagers will fall silent forever. That ending is inevitable. But even when they stop speaking to us, their journeys will have only just begun. In roughly 40,000 years, Voyager 1 will pass near a star in the constellation Camelopardalis. Voyager 2 meanwhile, will drift about 1.7 light-years from the star Ross 248 in the year 296,000 and about 4.3 light-years from Sirius sometime after that. By then, Earth may be long gone, but these small, tireless explorers will still be wandering the Milky Way, lonely messengers of a species that once looked up and dreamed of touching the stars. And if, by some unimaginable chance, they are ever found by intelligent beings in some far-off corner of the galaxy, they will carry with them a gift, the Golden Records. Each record is an audio-visual time capsule, containing photographs of our world, its landscapes, and its countless life forms, the sounds of whales singing and babies crying, music ranging from Mozart to Chuck Berry to traditional folk songs, and greetings in 55 languages. It is a message across time and space, offering strangers a glimpse of who we are and what life on Earth is like. For us, there will come a day when we must finally say goodbye to these old friends. But perhaps the Voyager mission will not be our last brush with the stars, only the first chapter in a much longer story of exploration. Is the universe something we can never escape from? Imagine for a moment that we managed to overcome the greatest barrier of all, the speed of light, and set off toward the farthest possible edge of space. What would we find there? Would it simply be more space stretching endlessly? Would we encounter infinite planets, stars, and galaxies without end? Or, in a strange twist of cosmic geometry, could we somehow loop back and end up right where we started? Amazingly, scientists tell us that all of these possibilities could be true. Which one is correct depends on the very nature of the hidden structure that surrounds us, a hidden world we cannot directly see. Let's venture into the mysterious territory of four-dimensional space as we tackle one of the most profound questions ever asked. What is the true shape of the universe itself? But before we can answer that, we need to talk about something equally mysterious: infinity. You've probably already met infinity in mathematics. It's not a single number. It's the idea of something so large that it has no end. No matter what number you think of, I can always add one more, and then one more again. That's the essence of infinity. There's always something beyond. When we apply this to the universe, things get a little mind-bending. So far, we have found no signs of an edge to space. It might be that there is always another star, another galaxy, and another cluster of planets no matter how far we go. But for human minds, which are used to living in a world with edges, boundaries, and endings, the thought of an infinite universe can be both thrilling and unsettling. Yet as we have built more and more powerful telescopes, pushing our vision deeper into the darkness, we keep making the same astonishing discovery. Even the blackest, most empty patches of the night sky are brimming with countless stars and galaxies. Infinity, once a philosophical idea, is starting to look like something we might have to accept as a real feature of our universe. But here's a surprising twist. Even if the universe goes on forever, that doesn't necessarily mean it contains an infinite number of unique things. That sounds contradictory, but I'll explain. In fact, when it comes to the possible shapes of the universe, scientists tell us there are three main possibilities: a flat universe, a spherical universe, and a hyperbolic universe. Now, let's explore them one by one. Imagine drawing a grid of straight lines in every direction, lines that either stay perfectly parallel or meet at perfect right angles. In a flat universe, this is essentially what reality looks like. If such a universe is infinite, it simply stretches outward in all directions, forever and ever, without looping back on itself. That might sound a little boring, and indeed it's the simplest option. Interestingly, this is also closest to how we perceive space most of the time. Planets, stars, and galaxies appear to lie along straight lines from our point of view. We don't usually notice any large-scale curving or bending. Now imagine bending those straight lines so that they always curve toward each other. The only way to draw such a universe is to put it on the surface of a sphere. On a sphere, parallel lines can't exist. Sooner or later, all lines meet. In this kind of universe, if you travelled in what you thought was a straight line, you would actually be moving along a gigantic curve. Eventually, without ever turning around, you'd find yourself back where you started. It's a bit like those old video games where your character walks off one side of the screen and instantly reappears on the other side. Here's a wild thought. In a spherical universe, if we had unimaginably powerful telescopes and light could move much faster than it does, you might actually be able to look into space and see the back of your own head. This kind of universe has a finite number of unique objects, but it appears infinite because you keep encountering the same objects again and again as you loop around. And in a way, we already have some evidence for space behaving like this, at least in certain places. The intense gravity of massive objects like black holes and stars bends light into curves, just like the surface of a sphere does. Inside a black hole's event horizon, this kind of curved infinity becomes absolute. No matter what direction you travel, you eventually return, or more accurately spiral, toward the singularity at its heart. There is no escape. Now comes the trickiest one to imagine, the hyperbolic universe. In this version, lines don't stay parallel and they don't curve toward each other. Instead, they curve away from each other. And not just slowly, they spread apart faster and faster the farther they go. If you try to draw this, you quickly run into trouble, because space would have to expand exponentially in every direction. The only way to show it is to warp your drawing into strange shapes, or use clever distortions. One result of this geometry is truly bizarre. In normal two-dimensional space, you can have only 3 squares meet neatly at a corner. But in hyperbolic space, you could have 5 or more squares meeting at a single point, all fitting perfectly. This is not just a mathematical curiosity. If our universe were hyperbolic, it would mean that as you move through space, everything would seem to expand and spread apart at a dizzying rate, giving an entirely different structure to reality. Let's take a step back and really think about this. If our universe curves, what exactly is it curving around? When we talked earlier about the universe being spherical in shape, you might have wondered, there must be something it is bending or curving around. But here's the twist. The direction of that curve isn't about space alone, it's about time. In this model, every object in the universe is always moving forward along its own timeline. Up means forward in time, into the future. If something moves to the left or right instead of straight upward, that means it is travelling through space, getting physically closer to something else. Now here's where it gets fascinating. Suppose we introduce something very heavy, a massive object, like a planet or a star, into this model. Suddenly, those neat straight timelines begin to bend and twist around it. If you were a small object drifting happily along your straight arrow toward the future, and you wandered too close to that mass, your path would no longer point straight up. Instead, it would curve sideways toward the massive object. Why does this happen? There are several complex reasons, but the most important takeaway is this. Your once straight path through time has been altered. Now, just to keep going in a straight line, you would have to push yourself away from the planet. Otherwise, you would start falling toward it. That pull you feel? That's gravity. And this effect doesn't just act on you, it acts on the massive object itself. Even the planet's own atoms are slightly squeezed inward toward its centre, as if giant invisible hands were pressing on it from all sides. Now let's change gears and talk about something called hyperbolic space, a strange kind of geometry where the opposite effect occurs. Instead of timelines curving inward toward each other, they all spread apart. Imagine a world where every line moves away from every other line, where nothing ever converges. In this model, we could picture space as being curved while time remains perfectly straight. From your perspective, your own personal clock ticks normally, but the space around you is stretching. If we make space perfectly flat in the diagram, it's simply a matter of perspective. But here's the key difference. In hyperbolic space, even lines that start parallel will slowly drift farther and farther apart. Does that sound familiar? It should, because that is exactly what astronomers observe the universe doing on the larger scales. Inside galaxies, there's enough mass and gravity to keep stars, planets, and other objects bound together. But when we look beyond individual galaxies, we see something astonishing. Every galaxy is moving away from every other galaxy. Scientists explain this using a mysterious force called dark energy. But perhaps the simpler answer is that the universe itself is naturally hyperbolic. It's built to expand like this. And if that's true, the implications are mind-bending. A flat universe is already infinite. Travel 1 light year, and you simply find another light year of space ahead. But in a hyperbolic universe, the infinity is even more infinite. For every light year you travel, you don't just find 1 more light year of space, you find more than that. It's like stepping through one door and discovering that it leads to two more doors, each of which leads to two more, and so on without end. The possibilities in such a universe would be far greater than in ordinary flat space. But there's a catch. If the universe truly behaved this way, then given enough time, every other galaxy would eventually drift so far away that only our own galaxy would remain visible. So far, astronomers haven't seen evidence of large-scale hyperbolic geometry. Instead, measurements suggest that the universe is surprisingly flat. But even this leaves an intriguing possibility. What if the universe really is hyperbolic by default, but the presence of mass, planets, stars, galaxies, curves it inward just enough to perfectly balance the outward curve, making it look flat to us? In such a case, all three models, spherical, flat and hyperbolic, might be correct at the same time, each shaping different parts of reality. There is some evidence hinting that this balance might be true, but it's incredibly difficult to prove. In ancient times, small groups of humans would gather closely around a single flickering campfire. The warm glow of the fire pushed back the surrounding darkness, but beyond that light, the night was full of unknowns. They would wonder nervously about what might be hiding in the shadows beyond the fire's reach. In many ways, that feeling of mystery hasn't changed much even today. Our campfires have grown much bigger now. They stretch far beyond simple flames to powerful tools like gigantic telescopes. These telescopes, including the incredible James Webb Space Telescope, let us see across our entire planet and far beyond, to the very edges of the universe we can observe. But just like those ancient nights, there is always a limit where light fades and darkness takes over. Beyond that limit lies a boundary of the observable universe, a kind of invisible wall we cannot cross. This boundary is not just any edge. It's a cosmic barrier caused by the universe's rapid expansion. Parts of space beyond this boundary are moving away from us so fast that nothing, not even light, can travel back from there to here. That means nothing beyond that edge can affect us, and we cannot reach it either. It's like a vast, unbreakable horizon. Because of this, whatever lies beyond this boundary seems forever hidden, destined to remain a mystery. Or at least, that was what we believed, until scientists noticed something strange. In the year 2008, researchers studied hundreds of huge groups of galaxies called galaxy clusters. To their surprise, these clusters were all drifting together, moving towards a certain direction near the edge of our observable universe. What was stranger still was that this movement was faster than current scientific theories could explain. It was as if something massive, something invisible far beyond the edge of the universe was pulling them with an unseen force. This strange, large-scale motion stretching across billions of light years is called dark flow. But what exactly is dark flow? What might be causing it? And how does it change what we know about the universe? Now, let's dive into the mystery of dark flow and explore its mind-bending effects on our understanding of the universe's origin. Dark flow is a controversial subject among scientists, so let's begin with what we know for sure. Back in 2001, NASA launched a special satellite called the Wilkinson Microwave Anisotropy Probe, or WMAP for short. Its job was to map the cosmic microwave background radiation, the faint afterglow left over from the Big Bang itself. This radiation quietly fills all of space, carrying clues about how the universe began and what it looks like today. WMAP completed its map in 2010, although pieces of its data were shared earlier. This map changed how scientists think about the universe. It helped answer big questions like, how flat is the universe, and what portion of the universe is made up of ordinary matter, like stars and planets, versus mysterious stuff like dark matter and dark energy. One scientist named Alexander Kashlinsky, working at NASA's Goddard Space Flight Center, was especially eager to explore this data. He led a team that compared the WMAP map of the cosmic microwave background with the movement of galaxy clusters. They wanted to see if any unusual patterns appeared. Their method was tricky. They used a tiny effect called the kinematic Sunyaev-Zeldovich effect. Here's how it works. When the ancient cosmic microwave background radiation passes through a galaxy cluster, a huge hot group of galaxies, it picks up a tiny bit of energy. This energy boost happens because the hot gas in the cluster heats the radiation, or because the cluster's motion adds kinetic energy. The problem was that this boost is incredibly small, so small that scientists had to study many clusters and use careful statistical methods to spot it. They needed a very detailed map of the cosmic microwave background and data on 1,000 galaxy clusters to compare. When they did this, they found something surprising: a huge, coordinated flow of galaxy clusters moving in the same direction. This flow stretched for 2.5 billion light-years, a mind-boggling distance, and the clusters were moving at speeds between 600 and 1,000 kilometers per second. The direction they were drifting toward was near the constellations Centaurus and Hydra. The big mystery is there was nothing visible out there that could be pulling them. This suggested there must be a massive source of gravity somewhere beyond what we can see, possibly beyond the edge of the observable universe itself. This idea is bold and controversial, but first, is it even possible for something outside the observable universe to affect us with gravity? You might think not, because as we said earlier, nothing beyond that cosmic boundary can influence us directly, not even gravity, since space is expanding faster than light can travel. This means we lose the ability to interact with those distant regions. This loophole lies in something called cosmic inflation, a brief moment right after the Big Bang when the universe expanded incredibly fast. Scientists in the 1970s, like the American physicist Alan Guth, noticed a puzzle called the horizon problem. It showed that distant parts of the universe, which should never have met or shared information, looked remarkably similar in temperature and structure. Guth realized that if, at the very beginning, everything was close together and interacting, like mixing different colors of dye in water, then a brief period of extremely rapid expansion could spread everything out to where it is now. This period, called cosmic inflation, happened within a tiny fraction of a second after the Big Bang, about 10 to the minus 33 seconds. Even though this time was unimaginably short, the universe expanded by a factor of 10 to the 26th power during that instant. To put that in perspective, that's like going from the size of a tiny bacterium to the size of the entire Milky Way galaxy, almost instantly, faster than anything we can truly imagine. This cosmic inflation explains how all parts of the universe could have once been connected and influenced each other before drifting apart so rapidly that they are now unreachable. Some advanced physics theories involving ideas like scalar fields and false vacuum states describe this, but that gets very technical. What matters for us is that cosmic inflation offers a way to understand how something outside the observable universe might have once affected what we see now, including possibly the dark flow of galaxy clusters. Here is the main idea. This mysterious dark flow might be explained by what happened in the very early universe, before everything we know, even atoms, had fully formed. Back then, there could have been a particularly heavy and dense area in the much larger universe. Our small patch of the universe that we can see today, called the observable universe, might have been pulled gently but firmly towards that dense region because it had a lot of gravity. Then, a process called cosmic inflation happened. This is when the universe suddenly expanded very quickly and enormously. This rapid expansion stretched space so much that this heavy mass was pushed far beyond what we can observe now. It moves so far away that it no longer pulls on us directly with gravity. But because things that start moving usually keep moving, like a rolling ball on a hill, the clusters of galaxies that were tugged by that mass continue drifting quietly in that same direction. They are basically flowing along with this cosmic current, which scientists call dark flow. However, this idea is controversial and debated for two big reasons. The first reason is that for dark flow to exist, there needs to be a huge amount of unseen mass just beyond the edge of our visible universe. This means there would have to be many more stars packed much more tightly than our current models say is possible. But this goes against one of the main reasons scientists, like Alan Guth, originally suggested cosmic inflation, to explain why the universe looks mostly uniform and smooth. When we look around, the universe seems pretty even everywhere. Scientists say it is homogeneous, meaning matter is spread out fairly evenly no matter where you look. It is also isotropic, meaning if you add up the speeds and directions of everything moving in space, they cancel out, showing no preferred direction. Dark flow challenges this whole picture because it suggests that just beyond the horizon where we can see, things suddenly get uneven, that heavy mass still exists but we cannot see it. This idea feels strange and raises many questions. For example, if the universe is not actually uniform beyond what we see, did we just get incredibly lucky to live in a very flat, even patch? What does this mean for our understanding of how the universe formed and the role of cosmic inflation? After all, if inflation was supposed to explain why the universe is smooth and even, but it turns out it is not, that shakes up everything we thought we knew. The second big reason why dark flow is controversial is that it might not even exist. A NASA scientist named Kashlinsky and his team believe dark flow is real, but another group called the Planck team, using even better and more detailed maps of the cosmic microwave background, the afterglow of the Big Bang, from their advanced Planck satellite launched in 2009, 8 years after the earlier WMAP satellite, did not find any evidence for dark flow. They looked at data from 1,000 galaxy clusters and saw no signs of this mysterious flow. But Kashlinsky's team looked again at the Planck data and said they do see signs of dark flow. So, the debate is still going on. Kashlinsky and his team even announced they would dig deeper into the Planck and WMAP data to try to find more conclusive proof, but as of now, their findings have not been finalised or published. Until we have stronger evidence, it makes the most sense to assume dark flow might not be real, that there is no spooky, unseen mass lurking just beyond the edge of what we can see, pulling thousands of early galaxies toward it billions of years ago. Still, with all mysteries, it makes you stop and wonder. Science doesn't care about the easiest or most convenient answer. The truth is the truth, whether it is complicated or simple. Maybe one day we will discover for sure what lies beyond the visible universe and whether dark flow is real. But even then, when one mystery is solved, another will appear just a little further away. The darkness will move back, and a new cosmic boundary will show itself, inviting us to explore once more. The future of finding planets beyond our solar system, called exoplanets, is looking brighter and more exciting than ever before. Recently, scientists have uncovered completely new types of these distant worlds that challenge everything we thought we knew. Let's start with the smallest stars in the universe, called red dwarfs. These stars are incredibly common, making up more than 70% of all the stars scattered across space. Because they are so numerous, scientists became very curious about the tiny planets that might be orbiting them. So, in September of the year 2022, astronomers trained their powerful telescopes to take a closer look at these small worlds around red dwarfs. What they found was truly amazing. They discovered a brand new kind of exoplanet made roughly half of rock and half of water that could exist either as a liquid ocean or as solid ice. These planets likely formed far away from their stars, beyond what's known as the ice line, where it's cold enough for water to freeze. But over time, these watery worlds moved inward, closer to their stars, where we can now detect them. This discovery is huge because water is one of the key ingredients for life as we know it. While these planets are rich in water, scientists aren't sure if they're covered in vast oceans like Earth. Still, the possibility that one of these worlds could be the next Earth 2.0 fires the imagination and inspires hope in our search for life in the universe. Next, imagine a planet so massive and mysterious, it's like a hidden version of Jupiter lurking quietly in our galaxy. Well, astronomers have just found one. It orbits a star that's about 379 light-years away, a light-year being the distance light travels in 1 year. This enormous planet named TOI 2180b is already the talk of the scientific community. Why? Because this giant world takes a staggering 261 days to orbit its star, a much longer trip than most other giant planets found so far. Even more surprising is its temperature. It's a comfortable 170 degrees Fahrenheit on average. To put that in perspective, Jupiter and Saturn have chilly temperatures around minus 280 degrees Fahrenheit. This means TOI 2180b is like a warm bridge between the cold gas giants we know and other hot planets astronomers have discovered. How this planet ended up with such unique traits is still a mystery scientists are eager to solve. Now, picture a fiery world nicknamed the Hulk planet. This is TOI 1075b, located about 200 light-years from us. It's called the Hulk because its surface is a roiling sea of molten lava. Imagine rivers of glowing magma everywhere. This super-Earth is one of the heaviest ever found, with almost 10 times the mass of our own planet Earth. Being so close to its star means the surface reaches blistering temperatures around 1,922 degrees Fahrenheit. That's so hot any water would instantly turn into steam, and the atmosphere is filled with vaporized rock instead of air as we know it. But the Hulk planet is not just hot. It also orbits its star incredibly fast, completing one full year in just 14.5 hours. That's one of the shortest years ever recorded for a planet this massive. This thrilling discovery adds a fiery new character to the cosmic family of planets. Astronomers also stumbled upon a shocking group of 3 doomed planets. These gas giants, similar in size to Jupiter, are locked in a dangerous dance around stars that are slowly dying. Just 10 years ago, scientists never thought such planets could exist. These giants orbit so close to their fading stars that they are essentially on the edge of disaster. Take TOI 2337b as an example. This planet's orbit is unstable, and it's predicted to plunge into its star's fiery surface in less than 1 million years. While that's far beyond any human lifetime, the process is a spectacular example of the cosmic drama that plays out as stars near the end of their lives. The dying stars pull nearby planets closer, twisting their orbits and heating their atmospheres until they expand and change in density in strange ways. Despite the grim future of these planets, studying them helps scientists understand how planetary systems, including our own, evolve over billions of years. Now, here's a truly wild discovery. 2 blazing hot planets with atmospheres made of the heaviest element ever found on an exoplanet, barium. These 2 planets, called WASP-76b and WASP-121b, are super-Jupiters, giant gas planets that orbit extremely close to their stars. They are so hot that one side faces temperatures high enough to vaporize iron and other metals. What's fascinating is that the vaporized iron gets carried by winds to the cooler side of the planet, where it condenses and falls as iron rain. And the presence of barium, a metal 2.5 times heavier than iron, in their upper atmospheres is a total mystery scientists are still trying to solve. Imagine standing on such a planet, watching iron rain fall through skies heavy with barium. That would be both amazing and terrifying. Let's take a look at the football planet. Named WASP-103b, this ultra-hot exoplanet is more than 1,000 light-years away from Earth and has a shape unlike anything seen before. Its gravity is so strong and its star so close that the planet is stretched out like a giant football rather than a perfect sphere. Thanks to precise measurements taken while the planet passes in front of its star, astronomers captured this unique stretching for the very first time. This snapshot of a planet in motion is giving scientists important clues about how extreme gravitational forces shape these distant worlds. It's a remarkable discovery that helps us understand the amazing variety of planets out there in the vast universe. Now, let's explore a truly fascinating world called VHS 1259b. It's a mysterious and strange planet far beyond our own solar system, filled with wonders that seem almost like science fiction, but it's very real. Imagine a place where the clouds floating in the sky are not made of water vapor like on Earth, but of tiny particles similar to sand, and above those sandy clouds the sky glows a deep, endless red. This incredible discovery was made by some of the smartest scientists working at NASA who study planets outside our solar system, called exoplanets. But VHS 1259b is not just any exoplanet. It belongs to a special kind of object known as a brown dwarf, something that's neither fully a planet nor a star. In fact, it is almost 20 times as heavy as Jupiter, the largest planet in our own solar system. That makes it way too big to be considered a normal planet, but it doesn't shine brightly like a star either. It's a cosmic mystery, an in-between kind of world that scientists are still trying to understand. What really makes VHS 1259b stand out is its unusual atmosphere. Scientists found that this strange planet is covered in thick clouds made of tiny silicate grains. These are basically minerals like sand floating high up in the air. This is the very first time anyone has seen clouds like this on a planet outside our solar system. It's a discovery that changes how we think about the skies of distant worlds, and it opens up new ideas about the kinds of environments that exist across the universe. Who knows? Maybe some of these faraway places could even hold clues about life beyond Earth. And so, the year 2022 was a remarkable time for space exploration. packed with amazing new discoveries about exoplanets like this one. But this is only the start of our journey. As scientists continue to look deeper into the vastness of space, exploring stars and planets far beyond our reach, we can only wonder what incredible secrets the cosmos will reveal next. The zodiacal light is a very faint, gentle glow you can sometimes see in the night sky, especially when the sky is very dark and clear. People also call it false dawn, when it appears just before the real sunrise. This soft glow is actually sunlight, but not the direct kind that shines straight from the sun. Instead, it is sunlight scattered, or bounced around, by tiny dust particles floating between the planets in our solar system. These dust particles catch the sunlight and spread it out, creating a faint triangular-shaped glow that seems to stretch upward from where the sun has just set or is about to rise. This glowing triangle appears along the zodiac, which is the path the sun appears to follow across the sky throughout the year, passing through the 12 famous constellations like Leo, Scorpio, and Taurus. The zodiacal light is brightest near the sun's position, but it can be seen as a dim band of light stretching along the entire path of the sun's movement, called the ecliptic. In fact, this light fills a large part of the sky and is one of the natural sources of light we see on a clear, moonless night. There is a related but slightly different faint glow called the Gegenschein, or counterglow. This is light from the sun bouncing off dust directly opposite the sun's place in the sky, and it looks like a faint oval-shaped patch of brightness. Even though the zodiacal light is part of the natural night sky's light, it is usually very faint. This means it is often hidden or drowned out by brighter lights, such as the moon, or city lights from towns and cities, what astronomers call light pollution. The dust that causes the zodiacal light is part of a large, thick cloud of tiny particles spread out across the solar system. This cloud is shaped like a flat pancake and lies mostly along the ecliptic plane, the imaginary flat disk where most of the planets orbit the sun. The dust particles themselves are very small, ranging from about 10 to 300 micrometers across. To give an idea, a micrometer is 1/1,000,000th of a meter, so these particles are incredibly tiny, with masses from about 1 nanogram up to several millionths of a gram. Back in the 1970s, two spacecraft called Pioneer 10 and Helios helped scientists understand more about this mysterious glow. They discovered that the zodiacal light comes from sunlight scattered by the dust cloud in our solar system. Later, the Juno spacecraft sent images of tiny bits of space dust hitting it, showing that this dust stretches from Earth's orbit out to a special place near Jupiter, called the 4:1 orbital resonance, about 2.06 astronomical units from the Sun. The data from Juno suggested that some of this dust might come from Mars. However, other spacecraft that studied space dust, like Pioneer 11, Galileo, Ulysses and Cassini, did not find strong evidence that Mars is a big source of this dust. Instead, most dust comes from comets and asteroids. If you want to see the zodiacal light for yourself, the best time is in the middle latitudes of Earth. In spring, look toward the western sky after the evening twilight has completely disappeared. In autumn, look toward the eastern sky just before the morning twilight begins. It looks like a tall, glowing column that is brighter near the horizon and tilted at the same angle as the ecliptic. The dust particles scatter sunlight mostly forward, meaning the light shines brightest when you look toward the sun's direction, but when the sun itself is just below the horizon and hidden from view. That is why the zodiacal light is most visible just before sunrise or just after sunset. Although this band of dust covers the entire zodiac or ecliptic, the dust farther away from that flat path is nearly impossible to see, except when looking almost directly toward the sun. Near the horizon, when the sun is just below it, the zodiacal light appears wider and stronger. Scientists have debated where this dust actually comes from for a long time. For many years, they thought it came from the tails of active comets and from collisions between asteroids in the asteroid belt. But many meteor showers we see in the sky don't have any known active comet as their source. Today, researchers believe that over 85% of this dust comes from pieces breaking off so-called Jupiter family comets. These comets have orbits around the Sun that take less than 20 years to complete. When they are not actively releasing gas or dust, they are called dormant, but they might start shining again someday. A detailed computer model of the zodiacal cloud showed that the dust must come from orbits that come close to Jupiter, to explain the thickness of this dust cloud around the ecliptic. Dust from meteoroid streams, the streams of particles that cause meteor showers, is much bigger, between 300 and 10,000 micrometers in size. Over time, these larger particles break down into the smaller dust grains that make up the zodiacal light. There is a natural force called the Poynting-Robertson effect that slowly pulls dust particles into more circular orbits, while gradually making them spiral inward toward the Sun. Because dust is slowly lost this way, there must be a steady supply of new dust particles to keep the zodiacal cloud going. Scientists think that dust from comets and from asteroid collisions mostly keeps the cloud full, creating both the zodiacal light and the Gegenschein. The dust particles can get smaller by bumping into each other or through space weathering, changes caused by solar wind and radiation. Once particles shrink below about 10 micrometers, they get pushed out of the inner solar system by sunlight's pressure. But then new dust comes in, mostly from comets falling inward. Around other stars, similar dust is called exozodiacal dust. This dust can make it harder for astronomers to see planets around those stars because it creates a kind of noise in their observations. Interestingly, the presence of this hot dust or debris disks around other stars might even hint that planets exist there, since planets tend to scatter comets inward, creating more dust. In 2015, the European Space Agency's Rosetta spacecraft, using its COSIMA instrument, provided strong evidence that the main source of interplanetary dust is indeed Jupiter family comets, like the famous comet 67 P. Churyumov-Gerasimenko. Meanwhile, data from the Juno mission confirmed that dust near Earth probably comes from sources within the inner solar system, with Mars being the best fit for that local origin. The beautiful glow we call zodiacal light happens because sunlight bounces off tiny dust particles that float around inside our solar system. These tiny bits of dust are often called cosmic dust. Since the light we see comes from the sun shining on these dust particles, the light has the same colours and qualities as sunlight itself. This cosmic dust is not scattered randomly everywhere, but is gathered in a special lens-shaped cloud of dust that surrounds the sun. This cloud stretches far beyond Earth's path as it orbits the sun. Scientists call this cloud the interplanetary dust cloud. Most of this dust is found near the flat plane in which the planets travel around the sun, called the ecliptic plane. That is why, when you look at the zodiacal light, you usually see it stretching along the same path where the sun, moon, and planets move across the sky. Interestingly, the amount of dust needed to create this faint glow is very small. Imagine the dust particles were about 1 millimeter wide, each reflecting light as well as the moon's surface does. In that case, each dust particle would be about 8 kilometers away from the next one. That is a huge distance for something so tiny. This shows just how thinly spread the dust really is. There is a related bright spot called the Gegenschein, which appears in the sky directly opposite the sun from Earth's viewpoint. Scientists think this glow happens because the dust particles there are fully lit by the sun, shining at their brightest phase, just like a full moon. In more detail, researchers Nesvorny and Jenisken studied how these dust grains behave. They found that dust grains about 150 micrometers across hit Earth at speeds averaging around 14.5 kilometers per second, with some coming in as slowly as 12 kilometers per second. Because these tiny comet dust particles are relatively slow and small, many of them can survive the fiery journey through Earth's atmosphere, sometimes becoming partly melted rather than completely burned up. This explains why scientists find unusual micrometeorites in places like Antarctica. These micrometeorites look very different from the larger meteorites that come from asteroids. In recent years, spacecraft flying through space have helped us see that the zodiacal light is not just a smooth glow. Instead, it contains detailed patterns and dust bands. Some of these dust bands come from broken pieces of specific groups of asteroids, while others come from trails left behind by comets. Historically, the zodiacal light has fascinated people for centuries. According to the famous explorer and scientist Alexander von Humboldt in his work Cosmos, ancient Mesoamerican peoples knew about the zodiacal light long before the year 1500. The first written report about it in Europe may have been by Joshua Childrey in the year 1661. Later on, in 1683, the well-known astronomer Giovanni Domenico Cassini studied this mysterious glow and suggested it was caused by dust particles orbiting the Sun. Some accounts say Cassini's student, Nicolas Fatio de Duillier, gave the first detailed explanation in 1684, encouraged by Cassini to explore the zodiacal light. A more modern chapter in the study of zodiacal light involves an unexpected figure, Brian May, the lead guitarist of the rock band Queen. In the year 2007, Brian May finally completed his long-delayed university thesis titled A Survey of Radial Velocities in the Zodiacal Dust Cloud. He had started this research 36 years earlier, but paused it to focus on his music career. He was able to finish and submit the thesis because very little new research had been done on the topic during that time. May said that studying zodiacal light became popular again in the early 2010s. Zodiacal dust clouds are not unique to Earth's neighbourhood. Other planets, like Venus and Mercury, have also been found to carry rings or clouds of dust along their orbits, showing that this glowing dust is a common feature around the Sun. A Type Eax supernova is a very rare and unusual kind of Type Ia supernova. Unlike typical Type Ia supernovae that completely blow apart their white dwarf stars, a Type Eax supernova leaves behind a leftover star, often called a zombie star, because it somehow survives the explosion instead of being totally destroyed. These Type Eax supernovae are quite similar to the regular Type Ia supernovae, but they differ because their explosions throw out material at lower speeds and shine less brightly overall. Scientists estimate that Type Eax supernovae happen somewhere between 5 and 30% as often as regular Type Ia supernovae. By the month of October, in the year 2014, astronomers had found about 30 supernovae belonging to this special category. Here's how they happen. Imagine a pair of stars closely orbiting each other, a binary system, where one star is a white dwarf, a dense, dead star, and the other is a normal companion star. The white dwarf pulls material away from its partner, slowly stealing gas and matter. In a normal case, the white dwarf would keep gaining mass until it hits a critical limit, which triggers a huge fusion explosion that completely blows it apart. But in a Type Eax supernova, the explosion is weaker, and the white dwarf loses only part of its mass instead of being completely destroyed. One famous example of a Type Eax supernova is called SN 2012Z. It happened in a galaxy named NGC 1309. This supernova was discovered by 3 astronomers, Bradchenko, Weidong Li, and Alex Filipenko, using a special telescope called the Katzmann Automatic Imaging Telescope on the 29th of January 2012 during a search for supernovae at the Lick Observatory. Scientists have a detailed idea of how SN 2012Z formed. Originally, it started as 2 large ordinary stars orbiting each other. The bigger star lost a lot of its hydrogen and helium gases to the smaller star and eventually became a white dwarf. The smaller star, now having gained more mass, grew larger and its outer layers surrounded the white dwarf. Then, the outer hydrogen layers of these overlapping stars were pushed away, leaving behind the helium core of the companion star and the white dwarf close together. After this, the white dwarf pulled some more matter from the helium core until it became unstable enough to explode as a supernova. But this explosion was weak, and the helium core survived, becoming what we call the zombie star, a stellar remnant still glowing after the blast. Remarkably, astronomers had pictures of the area before the explosion, allowing them to compare what it looked like before and after the supernova. This helped them study the whole explosion process. To test the idea of the zombie star, they observed the same area again a few years later. They noticed that the fading light matched what would be expected if a leftover star was still glowing from radioactive heating. However, fully explaining the entire brightness pattern over time was challenging, and no model fits perfectly yet. This discovery was a huge breakthrough. After many years of searching, SN 2012Z was the very first supernova where scientists could clearly identify the original star system before it exploded as a Type Eax supernova. Another example is SN 2008HA, which might also be a Type Eax supernova, but it was much weaker and less bright than SN 2012Z. More recently, on the 13th of September 2024, the Black GM telescope team spotted a new bright event in a galaxy called NGC 6744. At first, the star was thought to be a strange kind of nova, a smaller explosion. But after more study, scientists realized it was actually a faint Type Eax supernova. This might be the closest such supernova of this kind ever found. Going far back in history, Chinese and Japanese astronomers observed a bright new star in the sky in the year 1181 AD, now called SN 1181. Recently, an amateur astronomer named Dana Patrick discovered a nebula, a cloud of gas and dust, called Par 30, using the WISE space telescope. Astronomers later linked this nebula to SN 1181. At the centre of Par 30 is a star called Icarus 00500 plus 6713. This star is very special. It is an oxygen-rich Wolf-Rayet star formed when two white dwarfs, one made mostly of carbon and oxygen, and the other of oxygen, neon, and magnesium, merged and exploded as a type IX supernova. This makes Icarus 00500 plus 6713 a confirmed zombie star. Par 30 and its central star are the only known remains of a type IX supernova inside our Milky Way galaxy. A white dwarf is what remains after a star has used up most of its fuel and has collapsed into a very dense core. This core is made mostly of a special kind of matter called electron-degenerate matter, which means the electrons inside are packed so tightly that they resist further compression. Imagine squeezing the Sun's mass, the entire weight of our Sun, into a space roughly the size of Earth. That is how incredibly dense a white dwarf is. Unlike normal stars, white dwarfs no longer create energy through nuclear fusion, the process that powers stars like our Sun. Instead, the light they give off comes from leftover heat that slowly fades away over time. The closest white dwarf to us is called Sirius B, located about 8.5 light-years away. Sirius B is the smaller partner in a pair of stars known as the Sirius binary system. Scientists believe there are about 8 white dwarfs among the 100 star systems closest to the Sun. The strange faintness of these stars was first noticed more than 100 years ago, in the year 1910. The term white dwarf was given to them later, in the year 1922, by a scientist named Willem Jacob Luyten. White dwarfs represent the final stage in the life of stars that are not massive enough to become neutron stars or black holes. This is true for more than 97% of the stars in our Milky Way galaxy. When a star like our Sun finishes burning hydrogen in its core, the process that keeps it shining, it expands into a huge red giant and starts fusing helium into heavier elements like carbon and oxygen. But if the star isn't heavy enough to reach the very high temperatures needed to fuse carbon, about 1 billion degrees Kelvin, it will stop there. The star then sheds its outer layers, creating a beautiful glowing shell called a planetary nebula, and what is left behind is the dense core, the white dwarf. Most white dwarfs are made of carbon and oxygen. However, if the original star was heavier, between about 7 and 9 times the mass of the Sun, it can fuse carbon but not neon, leading to a white dwarf made mostly of oxygen, neon, and magnesium. On the other hand, very small stars may never fuse helium and can become white dwarfs made mostly of helium. Sometimes these helium white dwarfs form in binary star systems, where one star steals mass from the other. Since white dwarfs no longer produce energy through fusion, they have no internal heat source to stop gravity from crushing them further. Instead, they are held up by something called electron degeneracy pressure, a quantum mechanical effect where electrons resist being squeezed into the same state. This pressure is incredibly strong, which is why white dwarfs are so dense. But this support only works up to a certain point, about 1.44 times the mass of the Sun, known as the Chandrasekhar limit. If a white dwarf tries to get heavier than this, for example by pulling in mass from a companion star, it can no longer hold itself up. When that happens, it may explode in a brilliant event called a Type Ia supernova, caused by a sudden ignition of carbon inside. One famous example of this kind of supernova happened in the year 1006. When a white dwarf first forms, it is extremely hot, but it slowly cools over billions of years, giving off light that changes from bright blue-white to a cooler, redder glow. Eventually, after a very long time, the white dwarf's material will begin to freeze into a solid crystal, turning it into a cold, dark object sometimes called a black dwarf. Although no black dwarfs have been observed yet, because the universe is not old enough, the coolest known white dwarfs still shine at a few thousand degrees Kelvin. Studying these stars helps astronomers estimate the oldest possible age of the universe. The first white dwarf ever discovered was found in a triple star system called 40 Eridani, which contains a bright main star named 40 Eridani A, and a close pair, a white dwarf called 40 Eridani B, and a smaller red star called 40 Eridani C. This pair, B and C, was discovered by the famous astronomer William Herschel on the 31st of January, 1783. In the year 1910, scientists including Henry Norris Russell, Edward Charles Pickering and Williamina Fleming found that the faint star 40 Eridani B had a spectral type labelled A, meaning it looked white in colour, unusual for such a dim star. The spectral details of this white dwarf were officially recorded by Walter Adams in the year 1914. Soon after, the white dwarf companion to Sirius, known as Sirius B, was discovered. During the 19th century, astronomers were able to make very precise measurements of stars' positions in the sky. Friedrich Bessel noticed that Sirius and another star called Procyon appeared to shift positions regularly. In the year 1844, Bessel predicted both stars had unseen companions pulling them gravitationally. The orbit of Sirius's companion was calculated in 1851 by C.A.F. Peters. Finally, on the 31st of January 1862, Alvan Graham Clark spotted the hidden star next to Sirius, later identified as Sirius B. In 1915, Walter Adams announced that the spectrum of Sirius B was very similar to Sirius itself. In 1917, Adrian van Maanen discovered another white dwarf, now called Van Maanen's star, which is isolated, meaning it does not have a companion star. These three stars, 40 Eridani B, Sirius B, and Van Maanen's star, are called the classical white dwarfs, as they were the first known examples. Over time, many more faint stars with high proper motion, meaning they moved noticeably across the sky, were found, suggesting they were nearby white dwarfs. Willem Luyten was likely the first person to use the name white dwarf for this group of stars in the year 1922. The term became widely known thanks to the famous astrophysicist Arthur Eddington. Although many white dwarfs were suspected before, the first certain discoveries of non-classical white dwarfs only occurred in the 1930s. By 1939, astronomers had identified 18 white dwarfs. Luyten and other astronomers kept searching, and by 1950, more than 100 white dwarfs were known. By the end of the 20th century, around 1999, astronomers had catalogued over 2,000 white dwarfs. Since then, modern surveys such as the Sloan Digital Sky Survey have discovered over 9,000 more white dwarfs, most of them new to science. White dwarfs are fascinating stars that come in a variety of masses. NASA scientists have found some with masses as small as about 1/5 the mass of our Sun, and others as heavy as about 1 1/3 times the Sun's mass. But most white dwarfs have a mass close to just over half the Sun's mass, usually between half and 7/10 of the Sun's mass. Even though they have a mass similar to the Sun, white dwarfs are incredibly tiny compared to it. Their size is only about 1 to 2% of the Sun's radius. To put that in perspective, this size is very close to the size of Earth, which is about just under 1% the radius of the Sun. So imagine squashing a star with the Sun's mass into a space almost as small as Earth. That is a white dwarf. Because they cram so much mass into such a tiny space, white dwarfs are unbelievably dense. Their matter is packed about 1 million times more tightly than the average matter in the Sun. To give a sense of this density, a single cubic centimetre of white dwarf material weighs roughly 1 ton. That's like a very heavy car packed into a space smaller than a sugar cube. Typical densities for white dwarfs range from about 10,000 to 10 million grams per cubic centimetre, making them some of the densest objects in the universe. Only neutron stars and the still hypothetical quark stars are denser. White dwarfs were discovered to be incredibly dense, not long after astronomers first identified them. When a white dwarf is part of a binary system, meaning it orbits together with another star, scientists can figure out its mass by carefully observing how the two stars move around each other. This method was used on Sirius B, the famous companion to the bright star Sirius. By 1910, astronomers estimated Sirius B's mass to be just under 1 times the Sun's mass, and more modern measurements confirm it to be very close to exactly 1 solar mass. Because hotter objects shine more brightly than cooler ones, astronomers can estimate a star's brightness by measuring its surface temperature through its light spectrum. If they also know the star's distance from Earth, they can work out its true brightness, surface area, and size. When they did this for Sirius B and another white dwarf called 40 Eridani b, they found something very strange. These stars were very hot but surprisingly dim, which meant they must be incredibly dense. In 1916, astronomer Ernst Öpik calculated that 40 Eridani b had a density more than 25,000 times greater than the Sun's. Such a number was so shocking at the time that he called it impossible. By 1924, the famous astronomer Arthur Eddington pointed out that stars with such enormous densities should cause their light to be affected by gravity. Specifically, their light should shift slightly toward the red end of the spectrum, a phenomenon known as gravitational redshift. This was later confirmed in 1925 by measurements of Sirius B. What makes white dwarfs so dense is that their matter is not arranged like normal atoms connected by chemical bonds. Instead, they consist of a plasma, a superhot mix of free atomic nuclei and electrons that are not bound together. Because of this, the nuclei can be packed much closer than in normal matter, where electron shells keep atoms apart. Eddington wondered what would happen if the plasma in a white dwarf cooled down enough that atoms could no longer stay ionized. This mystery was solved in 1926 by physicist R. H. Fowler, using the new ideas of quantum mechanics. Electrons, which make up part of the white dwarf's matter, follow a special rule called the Pauli exclusion principle. This rule says that no two electrons can exist in exactly the same state at the same time. Instead, electrons fill up a range of energy levels, even at very low temperatures, forming what is called a degenerate electron gas, or Fermi C. This means even when a white dwarf cools down close to absolute zero, the electrons still have a lot of energy, and the star remains incredibly dense. When a white dwarf gets squeezed even more, electrons are forced into a smaller space, and the Pauli exclusion principle makes it harder for them to be pushed closer together. This creates a pressure, called electron degeneracy pressure, which acts like an invisible force holding the star up against its own gravity trying to crush it. Importantly, this pressure depends only on how tightly packed the electrons are, the density, not on the temperature. Because of this, heavier white dwarfs are smaller in size. The more mass they have, the more squished and dense they become. There is a limit to how heavy a white dwarf can be before it can no longer hold itself up. This is known as the Chandrasekhar limit, named after the brilliant scientist Subrahmanyan Chandrasekhar, who first calculated it in 1930. The limit says a white dwarf cannot weigh more than about 1.4 times the mass of the Sun without collapsing under its own gravity, possibly turning into a neutron star. This limit depends on the average weight of the atom's electrons inside the star. For typical carbon-oxygen white dwarfs, this number is roughly 2, leading to the familiar 1.4 solar masses. If a white dwarf were to gain enough mass, say, by pulling matter from a nearby star, it could reach this limit. When that happens, the star cannot support itself with electron pressure alone and starts to collapse. Usually, though, before this collapse, the temperature and density inside becomes so high that carbon fusion ignites, causing a powerful explosion instead of a quiet collapse. This explosion is called a type Ia supernova, which completely destroys the white dwarf. Scientists believe type Ia supernovae happen in a few ways, such as steady feeding from a companion star, collisions between two white dwarfs, or ignition in layers that then spread to the core. Although the exact cause is still debated, these supernovae are important tools for astronomers because they have almost uniform brightness and help measure distances across the universe. Because white dwarfs are so faint and small, they appear as a faint group of stars near the bottom of a special chart called the Hertzsprung-Russell diagram, which plots stars by their brightness and temperature. They should not be confused with red dwarfs, which are small, cool stars still burning hydrogen, or brown dwarfs, which are even cooler and do not sustain hydrogen fusion at all. The connection between how heavy a white dwarf star is, its mass, and how big it is, its radius, can be estimated using a special physics formula called the non-relativistic Fermi gas equation of state. This formula helps scientists understand how the size of a white dwarf changes as its mass changes. In this formula, the letter R stands for the radius of the white dwarf, M stands for its mass, and the little symbol that looks like a circle with a dot inside means that these values are measured compared to our Sun's mass or size. Another important term is the chemical potential, symbolized as Me, pronounced mu sub E, which is a thermodynamic property. It basically tells us how the energy inside the star changes when you add or take away a single electron. This chemical potential depends on what the white dwarf is made of. Scientists have made detailed computer models that include more complex physics beyond this simple formula, and when they compare these models to what they actually observe in the sky, they find they match quite well. This gives us confidence that the theory is on the right track. The term non-relativistic means that the formula assumes electrons inside the white dwarf are moving much slower than the speed of light. However, in reality, electrons in white dwarfs can move very fast, sometimes close to the speed of light. When that happens, the formula for kinetic energy, the energy of motion, needs to be changed to account for relativity, the physics of things moving at speeds near light speed. In this very fast or ultra-relativistic case, the simple Fermi gas model no longer finds a stable balance for the star. This situation leads to the idea of a maximum possible mass for a white dwarf star, known as the Chandrasekhar limit. Observations of many white dwarfs show that their masses are often close to the mass of the Sun, or less, which suggests either these stars started with similar masses to the Sun, or some powerful events caused them to lose mass. To get a more precise understanding of how mass and radius relate in a white dwarf, scientists use a more complex equation called the equation of state, which describes how the density, how tightly packed the matter is, and pressure, the force pushing outward, relate inside the star. By combining this with the hydrostatic equilibrium equation, which balances the inward pull of gravity against the outward push of pressure, they can calculate the exact structure of the white dwarf when it is stable. In the simpler, non-relativistic case, the size of a white dwarf shrinks as its mass grows. Specifically, the radius decreases in proportion to the inverse of the cube root of the mass. But when relativistic effects are included, this shrinking becomes more extreme, and the radius approaches zero at a specific mass, the Chandrasekhar limit. Beyond this mass, the electron pressure can no longer hold up the star against gravity, and the white dwarf can collapse or explode. Scientists have even created graphs to show this relationship. One curve, drawn in blue, shows the radius versus mass using the non-relativistic model. Another curve, in green, includes the relativistic corrections. Both treat the white dwarf as a very cold gas of electrons in balance with gravity. In these graphs, size is measured compared to the Sun's radius, and mass compared to the Sun's mass. They also assume that on average every 2 protons or nuclei share 1 electron, an average molecular weight per electron of about 2. All these calculations assume the white dwarf isn't spinning. If it spins, the balance changes slightly because the star experiences an outward centrifugal force, like when you spin a ball on a string. If the star spins evenly, its maximum mass increases just a little bit. But if it spins unevenly, and there is no internal friction, viscosity, as early scientist Fred Hoyle pointed out in 1947, there might be no limit to how heavy it can get while remaining stable. However, not all such spinning stars would remain stable in reality. Scientists have studied in detail how spinning affects the size and shape of white dwarfs, using advanced mathematics. They have also explored the detailed structure of their outer boundaries. The matter inside a white dwarf is very special. It is called degenerate matter, where electrons are packed so tightly that they cannot easily absorb light. Because absorbing a photon, a light particle, requires an electron to jump to a higher energy level, and sometimes those energy levels are not available. White dwarfs have very low opacity, meaning light passes through them more easily than in normal stars. This results in low radiative heat transfer inside the star. However, white dwarfs conduct heat very well, so their insides remain almost the same temperature throughout as they slowly cool down. Right after forming, the temperature inside a white dwarf is extremely hot, about 100 million kelvins, but over time, it cools to below 1 million kelvins for the coolest white dwarfs known. Around this hot core, a thin outer shell of normal, non-degenerate matter exists. This outer layer is cooler and slowly shines light like a black body, a perfect emitter of radiation. This process means white dwarfs can be seen for a very long time, as their outer layers gradually radiate away the heat stored deep inside. The colour of the light white dwarfs emit varies widely, from a bluish-white colour similar to hot stars classified as O, B, or A types, to yellow-orange shades like cooler K or early M stars. Their surface temperatures range from more than 150,000 kelvins to just below 4,000 kelvins. According to the Stephan law, the brightness, luminosity of a star grows quickly as its surface temperature increases, roughly proportional to the temperature raised to the fourth power. This means white dwarfs can shine from over 100 times the brightness of the Sun to less than 1/10,000th of the Sun's brightness. Some hot white dwarfs, with temperatures over 30,000 kelvins, emit soft X-rays, which allow astronomers to study their atmospheres in great detail. White dwarfs also produce neutrinos, tiny, nearly massless particles, through a process called the Oort process. This neutrino emission cools younger, hotter white dwarfs by letting energy escape directly from inside the star. Neutrinos can pass through the star's matter almost without interaction, carrying away energy and speeding up cooling during roughly the first 20 million years of a white dwarf's life. Back in 1952, astronomer Leon Mestel explained that unless a white dwarf collects new material from a nearby companion star or another source, its light comes only from leftover heat stored inside. It does not generate new energy. Because white dwarfs are very small in size, they radiate heat slowly and can stay hot for a very long time. As they cool, their surface temperature drops, their light becomes redder, and their brightness fades. Since the star only loses heat through radiation, its cooling process slows down over time. Scientists have calculated the cooling times for typical white dwarfs made mostly of carbon and with a hydrogen atmosphere. For a white dwarf with about 0.59 times the mass of the Sun, it takes approximately 1.5 billion years to cool to a surface temperature near 7,140 kelvins. Cooling further by about 500 kelvins to around 6,590 kelvins takes an additional 300 million years, but the next two similar steps in cooling take longer, 400 million years to about 6,030 kelvins, and over 1 billion years to roughly 5,550 kelvins. Most white dwarfs observed have surface temperatures between 8,000 and 40,000 kelvins. However, white dwarfs spend more time at cooler temperatures than hotter ones, so we expect many more cooler white dwarfs in the universe. When astronomers take into account that hotter, brighter white dwarfs are easier to detect, they do find more cooler white dwarfs as they look deeper. This trend stops for extremely cool white dwarfs below about 4,000 kelvins, because the universe is only so old and there hasn't been enough time for white dwarfs to cool beyond that point. One of the coldest white dwarfs found so far, called WDJ 21474035, has a surface temperature around 3050 kelvins. By studying how many white dwarfs exist at different brightness levels, astronomers can estimate when stars first started forming in our part of the galaxy. Using this method, they estimate our galactic disk is about 8 billion years old. In many trillions of years, long after all visible white dwarfs have cooled, they will become black dwarfs, cold, dark stellar remnants no longer emitting light. None are thought to exist yet, as the universe is not old enough for any white dwarf to have cooled so much. At very low temperatures, below about 4,000 kelvins, white dwarfs that have hydrogen in their atmospheres are affected by a process called collision-induced absorption. This happens when hydrogen molecules bump into helium atoms, changing how the star shines in red and infrared light, making these old white dwarfs appear bluer than expected. White dwarfs with little or no hydrogen, like WDJ 21474035, don't show this effect and appear more yellow to orange. Inside the core of a white dwarf, the matter is a completely ionized plasma, a hot mix of atomic nuclei and electrons, initially behaving like a fluid. Scientists predicted in the 1960s that as white dwarfs cool further, their cores should crystallize, turning from a fluid into a solid, starting from the center. The crystals likely form a neat repeating pattern called a body-centered cubic lattice. In 1995, it was suggested that studying pulsations in white dwarfs could test this crystallization idea. Then, in 2004, observations of a particular white dwarf named BPM 37093 indicated that about 90% of its mass had turned solid. Other studies have found that the crystallized fraction could range from about 32 to 82%. When the core crystallizes, it releases latent heat, a kind of stored heat energy, slowing down the cooling of the star. Another possible way to explain why some white dwarfs cool slower than expected is a process called solid-liquid distillation. In this, heavier liquid parts sink while lighter crystals float upward, releasing gravitational energy. Also, chemical differences in the plasma mixture can release energy as the star cools. This extra energy release was confirmed in 2019 after scientists noticed a pileup of over 15,000 white dwarfs observed by the Gaia Space Telescope, where their cooling seemed to slow down at a certain point. Some white dwarfs have very low mass, less than 0.2 times the mass of the Sun, and are mostly made of helium. These are called extremely low-mass white dwarfs and usually form in binary star systems. Because they have thick hydrogen envelopes, leftover hydrogen fusion in a process called the CNO cycle can keep them hot for hundreds of millions of years. Additionally, these stars stay in a swollen proto-white dwarf phase for up to 2 billion years before settling into the typical cooling path of a white dwarf. Most white dwarfs are believed to be mainly made of carbon and oxygen deep inside. However, when we look at the light they send out using a technique called spectroscopy, we usually find that this light comes from a very thin outer layer, or atmosphere, that is almost entirely made of either hydrogen or helium. In fact, the main element found in this atmosphere is at least 1,000 times more common than any other element. Back in the 1940s, a scientist named Schatzman explained why this happens. White dwarfs have an incredibly strong gravity on their surface, so strong that it pulls heavier elements down below, while lighter elements like hydrogen and helium float to the top. This means the atmosphere we see is very pure in terms of its main element. This outer atmosphere is just the very top of a larger thin envelope surrounding the star. This envelope is what's left over from the star's outer layers during its earlier life stage called the asymptotic giant branch, AGB, phase. The envelope might also include some material the star has collected as it moves through space. Scientists think this envelope has a layer rich in helium, which makes up no more than 1/100th of the white dwarf's total mass. If the atmosphere is mostly hydrogen, then a very thin hydrogen layer sits on top of the helium one, with a mass about 1/10,000th of the star's total mass. Even though these outer layers are very thin compared to the whole star, they are very important because they control how the white dwarf cools down over time. Inside the white dwarf, electrons are packed so tightly that they behave in a special way called degeneracy. These degenerate electrons conduct heat very well, so almost the entire mass of the white dwarf stays at nearly the same temperature. White dwarfs are very hot inside. The core temperature of a white dwarf with a surface temperature between 8,000 and 16,000 Kelvin can range from about 5 million to 20 million Kelvin. The outer layers slow down how fast the star cools by blocking heat from escaping quickly. The first time someone tried to sort white dwarfs by the kind of light they give off was in 1941 by G.P. Kuiper. Since then, scientists have created and improved various systems to classify white dwarfs. The system we use today was introduced in 1983 by Edward M. Sion, Jesse L. Greenstein, and their team. It uses a special code starting with the letter D for dwarf, followed by letters that describe the main features in the star's spectrum, the range of light it emits, and sometimes extra letters for secondary features. Then comes a number that shows the temperature. This number is found by dividing 50,400 Kelvin by the star's temperature. For example, if a white dwarf only shows lines of neutral helium in its light and has a temperature of 15,000 Kelvin, it might be classified as dB3 or dB3.5 if the temperature measurement is very exact. If the star also has a magnetic field and shows signs of hydrogen, it could be called dBepi3. Sometimes question marks or colons are added if scientists are not sure about the classification. Most white dwarfs, about 80%, belong to the DA class, meaning their atmospheres are dominated by hydrogen. The next largest group, about 16%, is the Db class, with helium-dominated atmospheres. A very small group, less than 1%, are DQ white dwarfs that are hotter than 15,000 Kelvin and have atmospheres mostly made of carbon. Other classes like Db, Dc, Do, Dz, and cooler DQ white dwarfs also have helium-rich atmospheres. The type we see depends a lot on the temperature. Very hot ones between 100,000 and 45,000 Kelvin are called Du, and show helium that is singly ionized, meaning helium atoms missing one electron. Between 30,000 and 12,000 Kelvin, they are dB with neutral helium lines, and below 12,000 Kelvin, they appear featureless and are called DC. Scientists have even detected molecules of hydrogen gas, two hydrogen atoms bonded together, in the atmospheres of some white dwarfs. Some researchers have wondered if white dwarfs might have a hot outer layer similar to the Sun's corona, but searches using X-rays and radio waves have not found any evidence for this yet. Interestingly, a few white dwarfs have atmospheres that are not uniform. One side might be mostly hydrogen, while the other side is mostly helium. About 1/4 to 1/3 of white dwarfs show metal lines in their spectra, which is surprising. Since metals are heavy elements, they should quickly sink down inside the star. The best explanation is that these stars recently pulled in material from rocky objects like small planets or asteroids. Scientists can even figure out what these rocks were made of by studying the metal lines in the star's light. For instance, a study in 2015 looked at the white dwarf called TON 345 and found that the metals in its atmosphere matched those of a rocky planet that had lost its outer layers because of strong winds from the star when it was in its giant phase. Magnetic fields on white dwarfs can be extremely strong. In 1947, PMS Blackett predicted that a spinning, uncharged object like a white dwarf should generate a magnetic field connected to how fast it spins. This idea, sometimes called the Blackett effect, was never widely accepted, and even Blackett himself thought it was wrong by the 1950s. Later, in the 1960s, scientists suggested that the magnetic fields on white dwarfs come from the magnetic fields their original stars had before shrinking down. If a star had a magnetic field of about 100 Gauss, which is a measure of magnetic strength, when it shrinks to a white dwarf about 100 times smaller in size, its magnetic field would increase to about 1 million Gauss. The first magnetic white dwarf ever found was called GJ742, or GRW plus 78247. It was discovered in 1970 by a group of scientists, James Kemp, John Swedland, John Landstreet and Roger Angel, who noticed its light was circularly polarized, a sign of a magnetic field. This star's magnetic field is extremely strong, around 300 million Gauss. Since then, scientists have found magnetic fields in over 200 white dwarfs, with strengths ranging from about 2,000 to 1 billion Gauss. Many of these stars are identified using low-resolution spectroscopy that can detect fields stronger than 1 million Gauss. Scientists can also measure magnetic fields without looking at spectral lines by using techniques like circular polarimetry or radio wave observations. It's estimated that at least 10% of white dwarfs have magnetic fields stronger than 1 million Gauss. These strong magnetic fields may even allow a new kind of chemical bond, called perpendicular paramagnetic bonding, which is different from the usual ionic or covalent bonds, though spotting molecules bonded this way would be very difficult. In 2016, astronomers discovered the first white dwarf pulsar, a white dwarf acting like a pulsar, which is a spinning star that sends out beams of energy, within a system called AR Scorpii. Until then, all known pulsars had been neutron stars, but this discovery showed that white dwarfs can behave this way too. Another white dwarf pulsar was found in 2023. Scientists once thought that some white dwarfs might change their brightness very quickly, with cycles lasting about 10 seconds, but searches in the 1960s did not find any stars varying so fast. The first variable white dwarf ever found was HL Tau 76, discovered in 1965 and 1966. It changes brightness with a period of about 12.5 minutes. The reason this period is longer than first expected is that the brightness changes come from non-radial gravity waves inside the star. There are different types of pulsating white dwarfs. The DAV or ZC-CT stars like HL Tau 76 have hydrogen atmospheres and belong to the DA spectral type. The DBV or V777, her stars have helium atmospheres and belong to the DB spectral type. The GW Vir stars, sometimes split into DOV and PNNV types, have atmospheres rich in helium, carbon and oxygen. These are not exactly white dwarfs, but are in a transitional phase between giant stars and white dwarfs, sometimes called pre-white dwarfs. All these pulsating white dwarfs show small changes in their light, usually between 1 and 30%, caused by different vibration modes with periods lasting from several minutes to almost an hour. By studying these brightness changes, scientists learn a lot about what is going on inside white dwarfs. This field of study is called astroseismology. White dwarfs are what stars become when they reach the very end of their life cycle. Specifically, stars that started out with a mass between about 7/100 and 10 times the mass of our Sun. The exact makeup of a white dwarf depends on how heavy the original star was. Scientists studying the Milky Way galaxy believe that right now there are roughly 10 billion white dwarfs scattered throughout it. Interestingly, white dwarfs that weigh less than about 1/4 of the Sun's mass are always found paired with another star in a binary system. As white dwarfs get heavier, between half and 3/4 of the Sun's mass, fewer of them are found in pairs. About 34% of those in this range are in binary systems. These lighter white dwarfs mainly have cores made of helium. Scientists think that over a very, very long time, much longer than the universe's current age of around 13,800,000,000 years, these stars will slowly use up all their hydrogen fuel. They may spend some time as blue dwarfs before eventually becoming white dwarfs made mostly of helium nuclei. However, because this process takes such an unbelievably long time, astronomers believe that the helium white dwarfs we see today probably formed through other processes, mostly involving the loss of mass when two stars interact in binary systems. For those helium white dwarfs not in binary systems, several ideas have been suggested. They might have lost mass because of a large planet orbiting them, or because a companion star exploded in a supernova and stripped away material. Another possibility is that two stars merged together. These ideas are still being studied. Now, when the original star's mass is between about 1/2 and 8 times the Sun's mass, its core gets hot enough to fuse helium into heavier elements like carbon and oxygen through a process called the triple alpha reaction. But it never gets hot enough to fuse neon. Near the end of this phase, the star has a core made mostly of carbon and oxygen, or sometimes oxygen and neon, that no longer undergoes fusion. Around this core there are shells where helium and hydrogen continue to burn. In star classification charts, these stars sit on a part called the asymptotic giant branch. Eventually they shed most of their outer layers, creating a glowing shell of gas called a planetary nebula, leaving behind only the carbon-oxygen core, which becomes a white dwarf. White dwarfs that weigh more than about 1.05 times the mass of the Sun are called ultramassive white dwarfs. When these form from single stars, their cores are expected to be made of oxygen and neon. However, about 1/5 of ultramassive white dwarfs form when two white dwarfs merge. In that case, the core is mostly carbon and oxygen instead. For stars that are even more massive, their cores eventually become hot enough to fuse carbon into neon, and then neon into iron. These stars do not become white dwarfs. Instead, their cores grow so heavy that the pressure holding them up fails, causing the core to collapse and triggering a massive explosion called a core collapse supernova. This explosion leaves behind either a neutron star, a black hole, or something even stranger. Some stars with masses roughly between 8 and 10 times that of the Sun are heavy enough to fuse carbon into neon and magnesium, but not heavy enough to fuse neon further. These stars may leave behind white dwarfs made mostly of oxygen, neon, and magnesium, as long as their cores do not collapse or explode violently. Although only a few white dwarfs like this have been identified, evidence mostly comes from observing special kinds of novae, called oxygen-neon-magnesium, or neon novae. Their light spectra show unusual amounts of neon, magnesium, and similar elements, which suggests they formed by material falling onto a white dwarf made of these elements. Scientists have also proposed that a special kind of supernova called a type IAX, which involves helium falling onto a white dwarf, could change these stars. In this scenario, the explosion is not strong enough to destroy the white dwarf completely. Instead, only a small amount of its mass is blasted away, creating an asymmetric explosion that can send the leftover star, sometimes called a zombie star, shooting through space at very high speeds, known as hypervelocity. The heavier elements created in the partial explosion fall back onto the star's core, accumulating there. These iron core white dwarfs would be smaller than carbon-oxygen ones of the same mass, and would cool and harden more quickly. Once a white dwarf forms, it becomes very stable and will slowly cool down over an incredibly long time, eventually becoming a black dwarf, a theoretical star that has cooled so much it no longer emits light. If the universe keeps expanding as it is now, astronomers believe that in about 10 quintillion to 100 quintillion years, galaxies will lose their stars as they drift away into empty space. White dwarfs will mostly survive this galactic dispersion, though occasionally two white dwarfs might collide and create a new star or explode in a supernova called Type Ia. The lifespan of a white dwarf is believed to be related to the lifetime of protons, the tiny particles that make up atomic nuclei. Protons have been observed to last at least 1,000 trillion years. Some grand unified theories in physics predict proton lifetimes between 1,000 trillion and 1,000 trillion years. If protons decay, the mass of the white dwarf will slowly decrease over time until it eventually fades away completely. If protons do not decay, they might still disappear through other rare nuclear or quantum processes, but this would take an unimaginably long time, possibly up to a 1 followed by 200 zeros years. A white dwarf can also lose mass if it is near a companion star that steals its material or causes it to evaporate. This can shrink the white dwarf until it becomes something like a planet, perhaps a helium planet or even a diamond planet, orbiting the former companion star. Some scientists have suggested looking for Earth-sized planets orbiting white dwarfs with surface temperatures cooler than 10,000 Kelvin. In such cases, the habitable zone, where liquid water could exist, would be extremely close, about 0.005 to 0.02 astronomical units from the white dwarf, which is very near compared to Earth's distance from the Sun. Any planet in this zone would likely be tidally locked, always showing the same face to the star. Because white dwarfs are about the size of Earth, these planets passing in front of them would cause strong eclipses, making them easier to detect. However, newer studies suggest that such close planets might face very strong tidal forces from their stars, triggering runaway greenhouse effects that could make them uninhabitable. There are also questions about how these planets could get into such close orbits in the first place. It's unlikely they could survive being engulfed during the star's earlier red giant phase. Alternatively, if they migrated inward after the white dwarf formed, the intense tidal forces would likely heat and sterilize them, leaving only hot, lifeless worlds. Before a white dwarf gains so much material that it reaches the Chandrasekhar limit, the hydrogen-rich material falling onto its surface can ignite in a less violent explosion powered by hydrogen fusion. These explosions, called classical novae, can happen repeatedly as long as the white dwarf's core remains intact. There are also dwarf novae, which show smaller and more frequent brightening events caused by changes in the material swirling around the star, rather than by fusion reactions. In general, binary systems where a white dwarf is pulling matter from a companion star are called cataclysmic variables. Besides classical and dwarf novae, these systems include types known as polars and intermediate polars, which have very strong magnetic white dwarfs. Both fusion-powered and accretion-powered cataclysmic variables have been observed to emit X-rays. When a white dwarf star is part of a pair called a binary star system, and it pulls in material from its companion star, many exciting and dramatic events can happen. For example, the white dwarf might experience sudden bursts of brightness known as novae. In some cases, it can explode in an even more powerful event called a type Ia supernova. If the white dwarf is able to pull material from its partner quickly enough, it might also become a super soft X-ray source, shining brightly in X-ray light because it is burning this material on its surface. Besides these fireworks, other effects happen in such pairs. The gravitational pull between the two stars can cause them to interact closely, and their magnetic fields can influence how the white dwarf spins. In fact, the fastest spinning white dwarfs that astronomers have definitely measured are all found in binary star systems. The fastest known spinning white dwarf is the one in the system called CTCVJ 20563014. Sometimes two white dwarfs orbit each other very closely. As they circle one another, they slowly lose energy by sending out ripples in space-time called gravitational waves. Because of this loss, their orbits get smaller and smaller until eventually the two stars merge together. Now, a white dwarf that is alone and not spinning cannot be more massive than about 1.4 times the mass of our Sun. This limit is known as the Chandrasekhar limit, named after the scientist who discovered it. However, if a white dwarf is spinning very fast and unevenly, this limit can be a bit higher. In binary star systems, white dwarfs can keep gaining material from their companions, making themselves heavier and denser. As they get closer to that mass limit, something remarkable might happen. The white dwarf could either ignite a huge fusion reaction or collapse into a different kind of star called a neutron star. Scientists have come up with two main ideas to explain how type Ia supernovae begin, called the single degenerate and double degenerate models. In the single degenerate model, a white dwarf made mostly of carbon and oxygen slowly pulls mass from a companion star that is still a normal star, not a white dwarf. As the white dwarf grows heavier, its core becomes more squeezed and hotter. Because white dwarfs don't rely on normal pressure to hold themselves up, rather, they are supported by a strange quantum force. Heating the core doesn't make the star expand and cool down. Instead, the heat speeds up the fusion reactions inside, which creates even more heat, causing a runaway reaction. In just a few seconds, a powerful thermonuclear explosion happens, burning through much of the white dwarf and creating a type Ia supernova, which completely destroys the star. The second idea, the double degenerate model, involves two carbon-oxygen white dwarfs orbiting each other in a binary system. Over time, these two stars merge into one object that is heavier than the Chandrasekhar limit. This causes carbon fusion to ignite inside the merged star, leading to the same kind of powerful supernova explosion. In both cases, the white dwarfs do not survive the explosion. They are completely destroyed by the blast.